What if I told you that the very same rules that govern the smallest particles in existence also shape the grandest structures of our cosmos? Picture this: a single electron existing in multiple places at once, somehow influencing the formation of galaxies billions of light years away. This isn't science fiction. This is the quantum cosmos, a breathtaking reality where the microscopic and the macroscopic aren't just connected, but are fundamentally intertwined in ways that defy our everyday intuition. We're about to embark on a journey that will challenge everything you thought you knew about how the universe works, from the bizarre behavior of atoms to the mind-bending vastness of spacetime itself. For centuries, we've viewed the quantum world and the cosmic realm as separate domains, one ruled by probability and uncertainty, the other by gravity and relativity. But what if these two worlds are actually two sides of the same coin? What if the key to understanding black holes, dark matter, and even the origin of the universe itself lies hidden in the strange, counterintuitive laws of quantum mechanics? This convergence of scales isn't just academic curiosity, it's revolutionizing our understanding of reality itself, revealing connections so profound they're rewriting the textbooks of physics and cosmology. In this exploration, we'll uncover how quantum superposition might have seeded the entire cosmic web of galaxies, how entanglement could be weaving the fabric of spacetime together, and how the uncertainty principle might hold the secret to our universe's very first moments. We'll venture from the infinitesimal Planck scale to the observable horizon of our cosmos, discovering along the way that the universe is far stranger, more interconnected, and more magnificent than we ever imagined. So join me as we dive deep into one of science's most thrilling frontiers, where every revelation brings us closer to answering humanity's oldest questions about where we came from, what we're made of, and what ultimately awaits our extraordinary cosmos. At the subatomic level, reality operates according to a completely different set of rules than the ones we experience in our everyday lives. This is the quantum realm, a domain so small that 1 million atoms could line up across the width of a single human hair. Here, particles like electrons and photons defy classical logic. An electron isn't just a tiny ball orbiting an atom's nucleus. It exists as a cloud of probability, a wave of potential locations and states, only settling into a definite position the moment we attempt to measure it. This isn't a limitation of our instruments, it is the fundamental nature of reality at this scale. Particles can be in two places at once, a phenomenon known as superposition, and they can become mysteriously linked or entangled, so that affecting one instantly influences its partner, even if that partner is on the opposite side of the galaxy. This is the bizarre and counterintuitive world of quantum mechanics. Now, pull back that perspective way back. Shift your gaze from the infinitesimal to the infinite, from the quantum foam to the cosmic ocean. Here, we witness the majestic dance of galaxies, each containing hundreds of billions of stars swirling through the void, colossal black holes with gravitational pulls so intense that not even light can escape, anchor these galaxies and warp the very fabric of spacetime around them. We observe the universe expanding at an accelerating rate, driven by a mysterious force called dark energy. This is the domain of general relativity, where gravity sculpts the universe on its grandest scales, from the gentle curvature of a planet's orbit to the violent collisions of entire galaxy clusters. It appears to be a world of certainty, of predictable motion and immense forces, governed by the smooth geometry of spacetime. For the longest time, physicists treated these two worlds as separate kingdoms, each with its own ruler and its own set of laws. The quantum theory ruled the tiny domain of particles and forces, while Einstein's theory of relativity governed the vast arena of planets, stars, and galaxies. The language of quantum mechanics is probability and uncertainty, dealing in discrete packets of energy and fuzzy states of existence. The language of cosmology is geometry and gravity, dealing in continuous fields and the precise curvature of the cosmos. They seemed not only separate but fundamentally incompatible, two different descriptions of reality that refused to be merged into one. Yet, a growing body of evidence suggests this separation is an illusion, a consequence of our limited, human-scale perspective. The universe, in its elegant design, does not operate with two sets of rulebooks. The same fundamental laws that dictate how a single electron behaves are also, somehow, writing the story of the entire cosmos. The key to unlocking the universe's deepest secrets, the nature of the Big Bang, the inner workings of black holes, the mysterious identity of dark matter and dark energy, lies in bridging this profound gap. The quantum enigma is not confined to the micro-world. Its fingerprints are smeared across the macrocosmos, waiting for us to decipher their meaning. This is the great challenge and the great promise of modern physics, to weave these threads into a single, seamless tapestry of understanding. To truly appreciate this quest for unification, we must step back into the intellectual whirlwind of the early 20th century. Picture the scene. The sturdy, predictable clockwork universe of Newtonian physics was shattering, and in its place, two revolutionary but seemingly contradictory visions of reality were emerging. On one side, a young Albert Einstein was redefining our very concept of space, time, and gravity with his theory of general relativity, published in 1915. He envisioned a dynamic cosmos where matter and energy told spacetime how to curve, and that curved geometry, in turn, dictated how everything moved. It was a breathtakingly beautiful theory of the very large, perfectly describing the orbit of Mercury, the bending of starlight, and the evolution of the universe itself. Meanwhile, a separate group of brilliant minds, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others, were piecing together the bizarre rules of the quantum world. They found that at the atomic scale, certainty evaporated. Particles behaved like waves, waves behaved like particles, and you could never know both a particle's position and its momentum with absolute precision. This wasn't a theory about the curvature of space, but about probability waves, discrete packets of energy, and fundamental uncertainty. Einstein, despite his own role in founding quantum theory with his explanation of the photoelectric effect, was deeply troubled by this inherent randomness. His famous objection to Bohr that God does not play dice with the universe highlights the fundamental philosophical chasm that had opened up. He derided the notion of quantum entanglement as spooky action at a distance, a ghostly connection that violated the local, causal universe his theory of relativity described. And so, for decades, physics developed along two parallel tracks. It was as if scientists were using two different maps for two different territories. If you were studying the nucleus of an atom or how light interacts with matter, you reached for the map of quantum mechanics. Its strange rules were undeniable, powering the invention of the transistor and the laser. If your gaze was turned to the heavens, to galaxies, black holes, or the Big Bang, you used the map of general relativity. This pragmatic separation worked brilliantly for a time, allowing incredible technological and theoretical progress in both fields. But the deepest thinkers always knew this was a temporary fix. The universe is one entity, and a complete description of reality would require these two magnificent maps to be merged into one seamless atlas. The question was how. The first major cracks in this divided view began to appear not in a theory but in observation. In 1964, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, accidentally discovered a faint, persistent microwave static coming from every direction in the sky. This cosmic microwave background radiation was the cooled remnant of the Big Bang's first light, the afterglow of creation itself. This monumental discovery provided stunning evidence for an expanding universe that began in an incredibly hot, dense state. And this is where the paths of the micro and macro began to converge. Theorists realized that to understand the universe in its first fleeting moments, when all of existence was compressed into a volume smaller than an atom, you couldn't use general relativity alone. You absolutely needed quantum mechanics. The origin of the entire cosmos was, by definition, a quantum event. This was the pivotal turning point. Cosmologists began to seriously consider that the large-scale structures we see today, the vast web of galaxies and cosmic voids, might have been seeded by microscopic quantum fluctuations. Tiny, random ripples in the primordial quantum field, stretched to astronomical sizes by the universe's rapid inflationary expansion, could have provided the gravitational seeds for everything that followed. At the same time, particle physicists, using increasingly powerful accelerators, were probing the high-energy conditions that mimicked the early universe, discovering a zoo of new particles and forces that all obeyed quantum rules. The quest to understand the fundamental forces of nature, electromagnetism, and the strong and weak nuclear forces led to the development of quantum field theory, a framework that beautifully described how particles interact. But gravity, the architect of the cosmos, stubbornly refused to be quantized using the same mathematical tools. The stage was set. The century-long quest to bridge Einstein's graceful cosmos of space and time with Bohr's fuzzy, probabilistic quantum world had moved from a philosophical debate to the central, defining challenge of modern physics. This bizarre idea of existing in multiple states at once isn't just a theoretical curiosity confined to a lab. It's the first profound principle connecting the quantum world to the cosmos itself. To truly grasp how strange this is, let's revisit one of the most famous thought experiments in all of science, conceived by Erwin Schrödinger in 1935. He proposed a scenario where a cat is placed in a sealed box with a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the Geiger counter triggers the hammer to smash the vial, killing the cat. But here's the quantum twist. According to the rules of superposition, until we open the box and look inside, that radioactive atom exists in a blurred state of both having decayed and not decayed. Consequently, the poor cat must also be in a superposition, simultaneously alive and dead. Schrödinger didn't propose this because he thought it was realistic. He meant to show how absurd it seemed to apply quantum weirdness to our everyday, macroscopic reality. It highlights the central mystery: what exactly causes this cloud of possibilities to collapse into a single, definite outcome simply through the act of observation. Now take that perplexing notion and expand it to a scale so vast it defies imagination. Could the entire universe, or large parts of it, be in a state of superposition? This isn't just a wild speculation from science fiction. Physicists like Max Tegmark at MIT have seriously proposed that superposition is not merely a property of tiny particles, but could be a fundamental feature of reality at all scales. The reason we don't see tables, chairs, or cats in blurred states is a process called quantum decoherence. Essentially, objects constantly interact with their environment, bumping into air molecules, absorbing and emitting light, and these countless interactions continuously measure the system, forcing it to choose a definite state almost instantly. For a single, isolated electron, it can maintain its quantum weirdness for a surprisingly long time. but for a complex object made of trillions of atoms, decoherence happens in a tiny fraction of a second, making superposition effectively invisible to us. But what if we could isolate something enormous? Theoretically, there's no upper size limit to superposition. It's just exponentially harder to maintain as things get bigger and more complex. This leads us to the most breathtaking cosmic implication of all. Let's rewind time all the way back to the universe's first fleeting moments. In the initial instance after the Big Bang, the entire cosmos was smaller than an atom, a single, incredibly hot, dense point. At that scale, quantum rules were the only rules, and according to our best theories, this primordial universe was seething with quantum fluctuations. Tiny, random variations in energy fields, governed by the uncertainty principle, were constantly creating pairs of virtual particles that would flicker in and out of existence. In our everyday world, these fluctuations are negligible, but in that rapidly inflating infant universe, something miraculous happened. The fabric of spacetime itself expanded at an unimaginable rate, stretching those microscopic quantum fluctuations to astronomical sizes in less than a blink of an eye. What was once a tiny ripple in a quantum field became a vast ripple in the density of matter and energy across the cosmos. These magnified ripples, frozen into the fabric of the expanding universe, became the gravitational seeds for everything we see today. The slightly denser regions, where those random quantum fluctuations piled up a little more matter, began to pull in more gas through gravity. Over billions of years, these overdensities grew into the first stars, then galaxies, and eventually the immense galaxy clusters and the cosmic web of filaments and voids that structure our universe. The cosmic microwave background radiation, that ancient afterglow from the Big Bang, provides a snapshot of this process. When we map its tiny temperature variations, differences of mere millionths of a degree, we are essentially looking at a blown-up, astronomical-scale photograph of those primordial quantum fluctuations. The grand architecture of the universe, from the largest cluster of galaxies to the position of our own Milky Way, might ultimately trace its origin back to a random quantum event, a superposition of possibilities that became actualized as the universe expanded and cooled. This means the entire cosmic landscape could be the result of quantum possibilities writ large across the sky, a permanent testament to a reality where the possible and the actual are forever and deeply intertwined. If superposition challenges our notions of a single reality, then the second principle we must confront is perhaps even more baffling, a phenomenon so strange that even Einstein struggled to accept it. This is quantum entanglement, a mysterious and instantaneous connection that can form between particles, linking their fates no matter how far apart they are pulled. Imagine creating two electrons in such a way that their properties are inherently linked, like a pair of magical dice that always land on matching numbers. Now take one of these electrons on a journey to the farthest galaxy while keeping its partner here on Earth. According to quantum mechanics, if you measure the spin of the local electron and find it pointing up, its distant twin will instantly be found pointing down. The information about the state seems to travel between them faster than the speed of light, a notion that completely defies our classical understanding of cause and effect and the limits imposed by relativity. Einstein was deeply troubled by this. Along with his colleagues Boris Podolsky and Nathan Rosen, he wrote a famous paper in 1935 arguing that quantum mechanics must be an incomplete theory because it allowed for what he derisively called spooky action at a distance. He believed there must be some hidden variables, some deeper layer of reality we hadn't yet discovered, that would restore locality and common sense to physics. For decades, this remained a philosophical debate. But then, in the 1960s, physicist John Bell devised an ingenious theoretical test to determine who was right, Einstein or the quantum weirdness. Experiments conducted since then, with ever-increasing precision, have consistently confirmed the quantum view. Entanglement is real. That spooky action is an undeniable feature of our universe, demonstrated in labs across the world with particles separated by hundreds of miles. This isn't a flaw in our theories. It is a fundamental aspect of how nature operates at its most basic level. But the true wonder of entanglement isn't just its confirmation in a laboratory. It's the breathtaking possibility that this strange quantum connection might be woven into the very fabric of the cosmos on the grandest of scales. Consider one of the great puzzles of cosmology, the uniformity of the cosmic microwave background. When we look at the afterglow of the Big Bang, we see that the temperature is almost exactly the same in every direction we look, to within 1 part in 100,000. This presents a profound problem. The universe simply hasn't existed long enough for light, or any signal limited by the speed of light, to have traveled between these distant regions and equalized their temperature. It's as if two people on opposite sides of a vast concert hall, who have never spoken or exchanged a signal, suddenly stood up and began singing the same note in perfect unison. How did they coordinate? One compelling hypothesis is that quantum entanglement provides the answer. In the universe's first infinitesimal moments, all particles and energy were packed together in an incredibly tiny, hot volume. They were all interacting, all potentially entangled with one another. Then, during the period of inflation, space itself expanded at a rate far exceeding the speed of light, violently pulling these once connected regions apart over mind-boggling distances. But that initial quantum connection, that spooky link, may have remained intact. The uniformity we see today might not be the result of any signal traveling through space, but rather a relic of a primordial entanglement that was forged before space itself was stretched to its current immensity. The universe, in this view, didn't need to communicate to become uniform. It was born uniform, its distant parts already in a coordinated quantum state. This idea leads to an even more radical proposition. That entanglement might not just be a phenomenon within spacetime, but could actually be the very thing that creates the structure of spacetime itself. This is the heart of some cutting-edge theories in quantum gravity. The concept, sometimes called entanglement creating geometry, suggests that the fabric of space and its gravitational field emerge from a vast, complex web of quantum entanglement between the fundamental constituents of reality. Think of spacetime not as a fundamental stage, but as a tapestry. The threads of this tapestry are countless trillions of entangled quantum connections. What we perceive as a smooth, continuous geometry from a distance is actually the collective pattern of this underlying quantum network. In this picture, two particles that are entangled are not communicating across a gap in space. They are, in a very real sense, directly connected because the space between them is built from their connection. This turns our intuition completely on its head. The universe is not a collection of separate objects in a void that somehow interact. Instead, it is a single, profoundly interconnected quantum system where distance and separation are illusions born from a deeper, non-local reality. Entanglement becomes the cosmic glue, the hidden architecture that binds everything together, revealing a universe that is fundamentally and holistically one. If superposition and entanglement stretch our imagination, then the third pillar of our quantum cosmic bridge might be the most fundamentally unsettling of all, because it strikes at the very heart of what we can know about reality. This is Heisenberg's uncertainty principle, and it declares a fundamental limit to our knowledge of the universe. It states that there are certain pairs of properties, like a particle's position and its momentum, that we can never measure with absolute precision at the same time. The more accurately you pin down where something is, the less you can know about where it's going and how fast. It's not a limitation of our microscopes or our technology. It is a basic feature of the universe itself. It's as if reality has a built-in blur, a fundamental fuzziness that we cannot overcome. To grasp this, picture a hyperactive hummingbird zipping through a garden. Your eyes can follow its general path, its momentum, as it darts from flower to flower. But the exact instant you try to frame its location, to pinpoint it to a single petal, you lose all sense of its direction and speed in that frozen moment. Conversely, if you could somehow measure its incredible velocity with perfect accuracy, that measurement would require observing it over a span of time and space, making its precise position at any single instant impossible to define. This isn't just a quirk of hummingbirds or quantum particles. It is the very nature of a universe built on wave-like probabilities. Certainty, it seems, is a privilege we only experience at our large, slow, human scale. Now, let's scale this quantum fuzziness up to the absolute limit and rewind time to the very beginning of everything. In the first fleeting moments after the Big Bang, the entire observable universe was compressed into a space trillions of times smaller than a single atom. At that scale, the uncertainty principle wasn't a minor effect. It was the dominant law of the land. The universe was a seething, bubbling cauldron of quantum foam, where energy fields fluctuated wildly due to this fundamental uncertainty. Tiny, random virtual particles and antiparticles were constantly flickering into and out of existence, borrowing energy from the vacuum for the briefest of moments before vanishing again. In our calm, modern universe, these fluctuations are mostly negligible, but in that incredibly dense, hot primordial state, they were everything. This is where the theory of cosmic inflation provides the crucial link, the amplifier that takes these microscopic quantum jitters and stamps them across the entire sky. The theory proposes that a fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, inflating from subatomic size to something much larger in an unimaginably short time. And as space expanded faster than the speed of light, it stretched those tiny quantum fluctuations in the energy field along with it. A microscopic region that was ever so slightly denser due to a random uncertainty-driven fluctuation got stretched into a macroscopic region of slightly higher density. An area that was a tiny bit less dense became a vast underdense void. The universe effectively took a quantum-level fingerprint and blew it up to a cosmic scale, freezing these random irregularities into the very fabric of spacetime. These magnified ripples in density became the gravitational seeds for all future structure. The slightly denser regions had a bit more gravitational pull, slowly attracting more and more matter over hundreds of millions of years. They became the nurseries for the first galaxies, stars, and eventually the great cosmic web we observe today. The slightly less dense regions evolved into the vast, empty cosmic voids that separate these structures. When we look at the map of the cosmic microwave background from missions like Planck, with its beautiful, mottled pattern of hot and cold spots, we are literally looking at a baby picture of the universe, and those spots are the direct imprint of quantum uncertainty writ large. As the renowned physicist Stephen Hawking profoundly realized, this principle doesn't just apply to atoms, it governs the fate of galaxies. He applied it to black holes, showing how they could slowly evaporate by emitting radiation now named after him, and he understood that the universe's initial conditions were likely set by quantum uncertainty. This principle demonstrates that the grand, deterministic structure of our cosmos, the majestic swirl of galaxies, and the vast emptiness between them, may have its ultimate origin in a fundamental, inherent, and beautiful randomness at the heart of all things. Just when we think we've grasped the strange nature of the quantum world, it reveals yet another layer of mystery that forces us to question the very essence of what is real. This brings us to our fourth profound principle, wave-particle duality, the astonishing concept that every bit of matter and energy in the universe possesses a split personality, capable of behaving as both a solid particle and a spread-out wave. The most iconic demonstration of this bizarre behavior is the legendary double-slit experiment, a deceptively simple setup that has profound implications. Imagine a barrier with two thin, parallel slits cut into it. Behind it, we place a detector screen that lights up when something hits it. Now, if we fire a stream of tiny particles like electrons at this barrier, what would you expect to see? Classically, you'd predict two bright bands on the screen directly behind the two slits, as if we were spraying tiny bullets through the openings. But the universe doesn't play by classical rules. When we actually perform this experiment, something magical happens. We don't see two bands. Instead, we see a series of many light and dark stripes, an interference pattern. This is the unmistakable signature of a wave. It's exactly what happens when you throw two pebbles into a still pond. The ripples from each impact spread out, and where the peaks of the waves from one slit meet the troughs from the other, they cancel each other out, creating a calm, dark line. Where peak meets peak, they amplify, creating a bright line. Somehow, each individual electron is not going through one slit or the other. It is acting as a wave and going through both slits at once, interfering with itself on the other side to create this pattern. The electron is in two places at the same time. The plot thickens dramatically when we try to catch it in the act. If we place a detector at the slits to see which one each electron passes through, the magic vanishes. The moment we observe the electron's path, the beautiful interference pattern disappears. We are left with just two boring bands, as if the electrons were simple particles all along. It's as if the electron knows it's being watched and changes its behavior accordingly. This isn't just true for electrons. Photons of light, neutrons, and even entire atoms and large molecules have been shown to exhibit this same wave-particle duality. The act of observation itself seems to force a potentiality to become an actuality, collapsing the wave of possibilities into a single, definite particle. Now, let's take this mind-bending concept and expand it to its ultimate limit. If the fundamental building blocks of reality have this dual nature, could it be that the cosmos itself exhibits a form of wave-like behavior? This isn't as far-fetched as it might seem. Some of the most ambitious theories in physics, particularly those seeking a theory of quantum gravity, are beginning to propose exactly that. They suggest that spacetime, the very stage upon which the cosmic drama plays out, might not be a smooth, continuous fabric as Einstein described, but might itself have a dual nature. In certain approaches, like loop quantum gravity, spacetime is proposed to be granular at the smallest possible scale, the Planck length. These tiny, discrete quanta of space could vibrate and interact in wave-like ways, meaning the geometry of the universe itself might be described by a wave function, a cloud of probability governing its possible shapes and curvatures. This leads to an even more radical thought. The large-scale structures we see in the universe, like the cosmic web of galaxies, might be the macroscopic result of wave-like phenomena that occurred on quantum scales during the universe's infancy. The distribution of galaxies isn't entirely random. It has a statistical pattern, a certain correlation that some physicists have playfully compared to an interference pattern written across the sky. Just as the double-slit experiment shows that a single electron has a wave nature that dictates where it is most likely to land, the initial quantum wave nature of the inflating universe may have dictated where galaxies were most likely to form billions of years later. We are, in a sense, living inside the frozen aftermath of a cosmic interference pattern. This principle strikes at the core of our classical intuition about a fixed, objective reality existing independently of us. Wave-particle duality suggests that what we call reality is not a predetermined set of objects with definite properties, but a tapestry of potentials and probabilities. The line between a solid substance and an ethereal field becomes blurred. An electron is not a thing that is sometimes a particle and sometimes a wave. It is something more fundamental that reveals a particle aspect or a wave aspect depending on our interaction with it. This implies that observation is not a passive process of seeing a world that is already there. It is an active process of participation that brings specific aspects of that world into being. From the moment we choose how to set up an experiment to observe a quantum system, to the way we point our telescopes at the ancient light of the cosmos, we are not just explorers of reality, we are collaborators in its creation, engaging with a universe that is far more fluid and responsive than we ever dreamed. The universe, it seems, is a master of the impossible, and its favorite trick is one that defies all classical intuition, a phenomenon where particles simply vanish from one side of an impenetrable wall and reappear on the other. This is quantum tunneling, and it's not magic. It's a direct consequence of the wave-like nature of reality we just explored. Think of it like this. If you were to roll a ball up a hill, you need to give it enough energy to reach the top and roll down the other side. If it doesn't have that energy, it simply rolls back. That's the classical world. But in the quantum realm, a particle isn't just a ball. It's also a wave of probability. And a wave doesn't just stop at a barrier it can't surmount. Instead, it tapers off, its amplitude decreasing exponentially but never quite reaching zero. There's always a tiny, non-zero probability that the particle will simply find itself on the other side of the hill, as if it had tunneled through it. It hasn't actually burrowed through the barrier. It has, in a very real sense, leveraged its inherent fuzziness to bypass the rules. We can witness this astonishing process at work in the very heart of matter itself. Inside large, unstable atomic nuclei, particles like alpha particles, which are simply bundles of 2 protons and 2 neutrons, are bound by the strong nuclear force. They are, in effect, trapped in an energy well. To escape, they would need to overcome a tremendous energy barrier. Classically, they should be imprisoned forever. But thanks to quantum tunneling, there's a small chance they will simply appear outside the nucleus, leading to the radioactive decay we call alpha decay. This is the process that powers smoke detectors, transforming a quantum quirk into a life-saving technology. Without tunneling, elements like uranium and radium would be stable, and the natural radioactive decay that heats the Earth's interior would cease to exist. Now, let's scale this microscopic marvel up to a truly cosmic arena, the heart of a star, deep within our sun, and every star like it, a fierce battle is raging. Atomic nuclei, all positively charged, desperately want to fuse together to create heavier elements and release the colossal energy that makes stars shine. But there's a problem. They fiercely repel each other due to the electromagnetic force. To overcome this repulsion and get close enough for the strong nuclear force to grab hold and fuse them, the protons need to be moving at incredible speeds, which requires temperatures of millions of degrees. Yet, even at the sun's core temperature of 15 million degrees, the protons are still not moving fast enough to classically overcome that barrier. The sun, by all classical accounts, should not shine. This is where quantum tunneling performs its most vital cosmic role. It provides the subatomic cheat code that makes life possible. A tiny fraction of the protons in the sun's core, moving with nearly enough energy, can simply tunnel through the electromagnetic repulsion barrier. This allows nuclear fusion to occur at a rate that sustains the star's energy output for billions of years. This process of stellar nucleosynthesis, powered by tunneling, is what forges the very elements of life. Every atom of carbon in your body, every atom of oxygen you breathe, and every atom of iron in your blood was once cooked inside the furnace of a long-dead star, all made possible because quantum tunneling allowed atomic nuclei to overcome impossible odds. The gentle warmth of sunlight on your skin is, at its origin, the tangible result of a quantum probability wave crashing through a barrier. The implications of tunneling reach even further back to the very birth of the universe. The theory of cosmic inflation proposes that the infant universe underwent a phase of exponential expansion, but a key question remains: what started it? How did the universe transition from a prior state into this inflationary phase? One compelling idea is that this transition was itself a quantum tunneling event. Imagine the early universe as a ball resting in a valley representing a high-energy pre-inflationary state. To get to the lower-energy inflationary state, it would have to roll over a mountain, an energy barrier it couldn't classically cross. A quantum fluctuation, however, could have allowed the universe to tunnel through that barrier, triggering the sudden, violent expansion that set the stage for everything to come. In this view, the entire observable cosmos might be the result of a single, incredibly fortunate quantum tunnel. This leads to the most profound speculation of all, that the universe itself could have tunneled into existence from literally nothing. The concept of nothing in quantum physics isn't just empty space. It's a seething foam of potentiality, where temporary fluctuations in energy can borrow from the void, following the uncertainty principle. Some theoretical models, like the one proposed by physicist Alexander Vilenkin, suggest that a quantum fluctuation could have tunneled a tiny bubble of spacetime into existence, a nascent universe from a state of no space and no time. While this remains a highly speculative and deeply philosophical idea at the very frontier of cosmology, it underscores the staggering power of quantum mechanics. It demonstrates that the rules governing the smallest particles don't just explain how stars shine. They may well illuminate the ultimate question of why there is something rather than nothing, revealing a cosmos where the impossible is not just probable but essential. Yet for all the light and structure we can see, astronomers have made a startling and humbling discovery. The stars, galaxies, and gas clouds we observe with our most powerful telescopes account for less than 5% of the universe's total content. The overwhelming majority of the cosmos is made of stuff we cannot see, two profound mysteries known as dark matter and dark energy. Together, they constitute about 95% of the universe's mass-energy budget, and their true nature remains the single greatest unsolved puzzle in all of physics. But what if the key to unlocking these cosmic secrets isn't found by building bigger telescopes, but by looking deeper into the quantum realm? The bizarre behavior of the smallest particles might just hold the clues to understanding the largest structures and the ultimate fate of everything. Let's start with dark matter, the universe's invisible scaffolding. We know it's there because of its gravitational pull. We can watch stars whipping around the centers of galaxies at speeds that should send them flying off into the void, but something unseen holds them in place. We can observe the way enormous clusters of galaxies bend the light from objects behind them, an effect called gravitational lensing, with a strength that far exceeds what the visible matter alone could produce. This ghostly gravitational glue is 6 times more abundant than all the normal atoms that make up you, me, and every star. But what is it? We have no idea. It doesn't emit, absorb, or reflect light. It simply interacts through gravity, weaving an invisible web that holds the cosmic architecture together. This is where quantum field theory enters the stage, offering its most promising candidates. For decades, the leading hypothetical particle has been the WIMP, or weakly interacting massive particle. As the name implies, a WIMP would be a relatively heavy particle that, besides gravity, interacts with normal matter only through the weak nuclear force, making it incredibly difficult to detect. The beautiful idea was that WIMP could have been produced in the hot, dense early universe in just the right abundance to account for the dark matter we see today. However, decades of incredibly sensitive experiments, conducted in deep underground laboratories to shield them from cosmic rays, have so far failed to find any definitive evidence for WIMP, leading physicists to broaden their search. This has brought a different quantum candidate into the spotlight, the Action, proposed to solve a completely different puzzle in particle physics. The Action is a hypothetical particle that would be incredibly light, trillions of times lighter than an electron, and behave less like a discrete particle and more like a pervasive, shimmering field filling all of space. If dark matter is made of actions, it would be a cold, wave-like substance gently flowing through the cosmos and through our bodies right now. The quantum properties of actions are so strange that detecting them requires not just brute force, but exquisite quantum ingenuity. Experiments are now using powerful magnetic fields and ultra-cold resonant cavities to try and convert a passing action into a faint microwave photon, a delicate process that hinges on the principles of quantum electrodynamics. The hunt for these quantum phantoms is a direct bridge connecting the abstract mathematics of particle physics to the gravitational dynamics of entire galaxies. Then there is the more recent, and in some ways even more perplexing, discovery of dark energy. In the late 1990s, two separate teams of astronomers made a Nobel Prize-winning discovery. Not only is the universe expanding, but that expansion is accelerating. Something is actively working against gravity, pushing galaxies apart at an ever-increasing rate. This something has been dubbed dark energy, and it makes up about 68% of the universe. The leading explanation, though it comes with its own set of profound problems, points directly back to the quantum vacuum. According to quantum field theory, what we perceive as empty space is not empty at all. It is a seething, bubbling foam of virtual particles, pairs of particles and antiparticles that spontaneously flicker into and out of existence, borrowing energy from the vacuum for the briefest moments allowed by the uncertainty principle. This quantum activity is believed to imbue every cubic centimeter of space with a certain energy, known as vacuum energy or a cosmological constant. This energy has a repulsive gravitational effect, which could perfectly explain the observed acceleration of the universe's expansion. There's just one colossal problem. When physicists try to calculate the expected value of this vacuum energy using quantum mechanics, their result is off by a factor of 1 followed by 120 zeros. It is arguably the worst theoretical prediction in the history of science. This staggering discrepancy suggests either a fundamental flaw in our understanding of quantum field theory, or that something is canceling out this vacuum energy in a way we don't yet comprehend. Solving this problem will require a complete theory of quantum gravity, a framework that successfully merges the laws of the very small with the laws of the very large. The quest to identify these dark components is now driving some of the most ambitious experiments on Earth and in space. Projects like the Large Underground Xenon experiment continue the search for WIMP in abandoned gold mines, while initiatives like the Action Dark Matter experiment use quantum amplification to listen for the faint whisper of an action converting into a photon. In space, the Euclid telescope is meticulously mapping the distribution of dark matter, and the evolution of dark energy across 10 billion years of cosmic history. Each of these endeavors is a testament to a powerful idea that the answers to the grandest cosmic mysteries are hidden in the quantum code of reality. To truly see the dark universe, we may not need a bigger lens, but a deeper understanding of how the ghostly whispers of the quantum world shape the destiny of the cosmos. For nearly a century, physics has been living with a profound and beautiful schism, a division between two incredibly successful but seemingly incompatible descriptions of reality. On one hand, we have quantum mechanics, which governs the world of the very small with its probabilities, uncertainties, and discrete particles. On the other, we have Einstein's general relativity, which masterfully describes the universe on its largest scales as a smooth, curving fabric of spacetime. Each theory works flawlessly within its own domain, powering our technologies and predicting cosmic events with stunning accuracy. Yet, when their territories overlap, in places of extreme density and gravity like the center of a black hole or the very first moment of the Big Bang, the mathematical frameworks break down completely, producing nonsensical answers like infinite densities. This glaring incompatibility tells us that we are missing a deeper, more fundamental theory, a single set of rules that can describe all of reality, from the quantum foam to the cosmic web. This grand pursuit, the search for a theory of quantum gravity, is arguably the greatest challenge in all of modern science. So why has this unification proven so incredibly difficult? The heart of the problem lies in the very different languages the two theories speak. General relativity is a classical theory. It is deterministic and continuous. It describes gravity not as a force, but as the elegant curvature of a smooth, four-dimensional spacetime continuum. Mass and energy tell spacetime how to curve, and that curved geometry tells objects how to move. It's a beautiful geometric dance. Quantum mechanics, however, is probabilistic and discrete. It deals in quantum-indivisible packets of energy and fundamental uncertainty. Its mathematical engine, quantum field theory, is built on particles existing against the static backdrop of a flat, fixed spacetime stage. The two concepts of spacetime are utterly at odds. When physicists try to apply the standard quantization rules to gravity, to chop the gravitational field into discrete packets called gravitons, the mathematics rebels, producing infinities that cannot be renormalized or smoothed away as they can for other forces. Gravity, it seems, refuses to be tamed by the same tools that worked for electromagnetism and the nuclear forces. This impasse has forced physicists to propose radically new visions of reality. One of the most ambitious and well-known is string theory. Imagine if the fundamental building blocks of the universe were not zero-dimensional points, but incredibly tiny, vibrating one-dimensional strings. Each different vibration mode of these strings would correspond to a different particle. One note in the symphony might be an electron, another a photon, and another, crucially, would be the graviton, the hypothetical quantum carrier of gravity. In this cosmic symphony, gravity is inherently woven into the theory's fabric, not added as an afterthought. String theory also requires extra spatial dimensions beyond the three we experience, curled up into shapes so small we never notice them, to make its mathematical consistency work. While breathtaking in its scope and mathematical elegance, string theory has been criticized for its lack of direct experimental predictions so far, making it a magnificent but still unproven castle in the air. Taking a completely different approach is loop quantum gravity. If string theory changes the actors on the stage, loop quantum gravity changes the stage itself. Pioneered by physicists like Carlo Rovelli, Lee Smolin, and Abhay Ashtekar, this theory does not attempt to quantize gravity within spacetime, Instead, it quantizes spacetime itself. The central idea is that space is not smooth and continuous, but is made of tiny, discrete, indivisible grains or loops. Picture the fabric of reality not as a smooth sheet, but as a vast, evolving network of a billion tiny interconnected threads, a spider's web of spacetime relationships. These loops define the minimum possible scale, the Planck length, below which the concept of distance loses all meaning. This granular structure of space naturally resolves the terrifying singularities at the heart of black holes and the beginning of the Big Bang, replacing them with a theoretical quantum bounce or a fabric so tightly woven that densities cannot become infinite. It's a more minimalist approach than string theory, working with just the 3 dimensions of space and 1 of time we know, but it provides a powerful and intuitive way to think about a pixelated universe. The stakes for finding this final theory could not be higher. A successful theory of quantum gravity would be the ultimate key to unlocking the universe's deepest secrets. It would allow us to peer past the event horizon of a black hole and understand its true core. It would take us back to the very first moment of time itself, to see if there was a beginning or if our universe emerged from a previous cosmic cycle. It would illuminate the ultimate fate of everything. Will the universe expand forever into cold darkness, collapse back in a big crunch, or something else entirely? It would finally explain the profound connection between the energy of the quantum vacuum and the acceleration of the cosmos driven by dark energy. This is more than an academic exercise. It is a quest to complete our map of reality, to write the final chapter in the story of the fundamental laws of nature, and in doing so, to understand our true place within this astonishing quantum cosmos. But perhaps the most radical and mind-bending proposal for how to bridge the quantum and gravitational worlds takes this idea of interconnectedness to its absolute limit, suggesting that our entire experience of reality might be nothing more than an elaborate illusion. This is the holographic principle, a concept so profound it challenges our most basic assumptions about the nature of space, dimension, and existence itself. The story of this incredible idea begins not with the birth of the universe, but with the enigmatic physics of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's event horizon, the point of no return, possesses a property called entropy, a measure of disorder or information content. This was shocking because it suggested that black holes weren't just simple, empty voids, but objects that somehow contained or encoded information. Stephen Hawking soon built on this, showing that black holes aren't completely black. They slowly radiate energy and evaporate over astronomical timescales through the quantum process that now bears his name. This led to a terrifying paradox. According to the fundamental tenets of quantum mechanics, information can never be truly destroyed. It might be scrambled, but it must be preserved. If you were to burn a book, in principle, every single letter in that book could be recovered from the precise state of the smoke and ashes, if only you had a powerful enough computer. But if you throw that same book into a black hole, and the black hole later evaporates into a faint mist of Hawking radiation, what happens to the information? Has it been lost forever, violating a core rule of quantum physics? This is the black hole information paradox, and it has stumped physicists for decades. The resolution proposed by theorists like Gerard T. Hooft and Leonard Susskind is the holographic principle. They suggested that the information about everything that falls into a black hole isn't lost inside its mysterious interior. Instead, it is perfectly encoded and preserved on the two-dimensional surface of its event horizon, like a cosmic fingerprint smeared across the point of no return. The three-dimensional interior, with all its contents, is somehow a projection of this two-dimensional data. To grasp this, think of an ordinary hologram, like the ones you might see on a credit card or a banknote. That shimmering, three-dimensional image of an eagle or a globe isn't actually three-dimensional at all. It is projected from a flat, two-dimensional surface etched with microscopic patterns. The depth, the parallax, the feeling of solidity, it's all an illusion created by light interacting with that 2D surface. The holographic principle boldly applies this same logic to our entire universe. It suggests that all the information needed to describe every star, every planet, every person, and every event within a volume of space, a region the size of a room or the entire observable cosmos, could be encoded on the two-dimensional boundary that surrounds it. Our rich three-dimensional reality, with its overwhelming depth and volume, might be nothing more than a projection, a holographic movie playing out on the distant surface of the cosmic sphere. This isn't just a nifty metaphor, it's a serious framework being explored in the quest for quantum gravity, particularly in approaches like string theory. The mathematics suggests that a universe with gravity in three spatial dimensions could be entirely equivalent to a quantum field theory without gravity operating on its two-dimensional boundary. Our tangible world of forces, matter, and gravity could be a holographic projection of a simpler, flatter world where there is no gravity, only quantum information interacting on a vast cosmic screen. This would mean that the true fundamental degrees of freedom, the ultimate bits of reality, reside on this lower dimensional surface. The depth we experience, the very feeling of being inside a three-dimensional space, is an emergent property, an illusion that arises from the complex way that information is processed and decoded. The implications of this for cosmology are staggering. It provides an elegant potential solution to the black hole information paradox. The information is never truly inside the black hole, so it doesn't need to be released. It was on the horizon all along. Furthermore, it offers a new way to think about the universe's origin. Perhaps the Big Bang wasn't an explosion in a pre-existing space, but the moment when the cosmic hologram first flickered to life, when the information on the boundary began processing and projecting the illusion of a vast, expanding interior. This principle blurs the line between the micro and the macro in the most profound way possible. The fundamental building blocks aren't tiny strings or loops of energy, they are bits of information. The universe at its core might be composed not of stuff but of data. The laws of physics could be the software, and the cosmos we see and feel is the magnificent, immersive output. It's an idea that transforms the universe from a place of things into a realm of meaning, where the deepest reality is written not in particles or forces, but in a simple, elegant code on the surface of everything. To grasp the sheer scale and importance of this rapid growth spurt, imagine the entire observable universe, which today spans over 90 billion light-years, starting out smaller than a single proton. In that first sliver of a second, a peculiar energy field, often called the inflaton field, is thought to have dominated the cosmos. This field possessed a unique property. It generated a powerful repulsive gravity, causing space itself to stretch at an exponential rate far exceeding the speed of light. In an almost incomprehensibly short time, a fraction of a second so tiny it's written as 10 to the power of -32 seconds, the universe inflated by a factor of at least 10 to the 78 in volume. It was the most violent and transformative event in all of existence, smoothing out the cosmos and setting the stage for everything to come. But within this incredible burst of expansion lay the seeds of all future structure, and they were planted by the random, unpredictable hand of quantum mechanics. Even in that hyper-energy, dense environment, the uncertainty principle still held sway. The inflaton field was not perfectly smooth and uniform. Like the surface of a pond on a windy day, it was roiling with tiny, random quantum fluctuations. Virtual particles flickered in and out of existence, creating minute, temporary hills and valleys in the energy field. Under normal circumstances, these fluctuations would be insignificant, vanishing as quickly as they appeared. But inflation acted like a cosmic amplifier, stretching these microscopic quantum wrinkles to astronomical proportions almost instantaneously. A tiny region of space that was ever so slightly denser due to a random fluctuation got stretched into a vast macroscopic region of slightly higher density. An area that was a tiny bit less dense became a gigantic underdense void. The universe effectively took a quantum-level fingerprint and blew it up to a cosmic scale, freezing these random irregularities into the very fabric of spacetime itself. A helpful way to visualize this is to think of a perfectly smooth balloon. Now draw a few tiny, random wrinkles on its surface with a fine-tipped marker. As you inflate the balloon to an enormous size, those once tiny, localized wrinkles are now stretched into vast, continent-sized patterns across the rubber. The minuscule has become monumental. In exactly the same way, the quantum jitters in the early universe were imprinted and magnified by inflation, becoming the grand blueprint for the cosmic web of galaxies we observe today. These magnified ripples in density were, in essence, the gravitational seeds for all future structure. The slightly denser regions had a tiny bit more gravitational pull, slowly attracting more and more matter over hundreds of millions of years. They became the nurseries for the first galaxies, stars, and eventually the great clusters and filaments we see. The slightly less dense regions evolved into the vast, empty cosmic voids that separate these structures. The most stunning confirmation of this incredible story comes from the oldest light in the universe, the cosmic microwave background radiation. This faint microwave glow, a cooled remnant of the Big Bang's first light, fills the entire sky. When satellites like NASA COBE, WMAP, and the European Space Agency's Planck meticulously mapped this radiation, they didn't find a perfectly smooth and uniform blanket of light. Instead, they found a beautiful, mottled pattern of tiny temperature variations, differences of mere millionths of a degree. These hot and cold spots correspond directly to those primordial density fluctuations. The hotter spots show us where the universe was a tiny bit denser. The colder spots show where it was a bit more sparse. This map is essentially a baby picture of the universe, taken when it was only 380,000 years old. And the pattern of those spots matches the predictions made by inflationary theory with spectacular precision. The statistics of the fluctuations, their distribution across the sky, are exactly what we would expect if they originated from quantum mechanical processes stretched by a period of exponential expansion. It is the most powerful evidence we have that the largest structures in the cosmos were indeed born from the smallest of quantum beginnings. This revolutionary idea was first proposed by physicist Alan Guth in 1980, although his initial model had technical issues that were soon refined by others, including Andre Linde and Paul Steinhardt. Guth realized that a period of rapid inflation could elegantly solve several major puzzles in cosmology at once, such as why the universe is so flat and uniform on large scales. But the most profound implication, which became clear later, was inflation's ability to transform quantum noise into cosmic structure. Andre Linde further developed the theory into what's called chaotic or eternal inflation, suggesting that inflation might not be a one-time event but an ongoing process, continuously giving birth to new, pocket universes within a vast multiverse. The work of these pioneers showed that the universe is not just connected to the quantum world, it is a direct and magnificent product of it. the grand, deterministic architecture of our cosmos, the majestic swirl of galaxies, and the vast emptiness between them, finds its ultimate origin in a fundamental, inherent, and beautiful randomness at the quantum scale. Inflation is the essential bridge, the cosmic amplifier that takes the whispers of the quantum world and turns them into the galaxy-shaping forces that define our universe. Yet for all their fearsome power and mystery, black holes are far more than just cosmic vacuum cleaners. They are the ultimate natural laboratories, the extreme environments where the two great pillars of modern physics, quantum mechanics and general relativity, are forced to confront one another in a dramatic and unavoidable clash. At the edge of a black hole, the smooth, geometric certainty of Einstein's spacetime collides head-on with the fuzzy, probabilistic uncertainty of the quantum world, and the results of that collision are forcing us to rewrite the fundamental rules of reality. To understand this cosmic battleground, we must first step up to the very precipice of a black hole, to a boundary known as the event horizon. This is not a physical surface, not a solid wall you could touch, but a mathematical point of no return. It is the invisible spherical shell surrounding the black hole where the gravitational pull becomes so intense that not even light, the fastest thing in the universe, can achieve escape velocity. Once anything, a particle, a spacecraft, or even a stray photon of light crosses this threshold, its fate is sealed. It is irresistibly drawn inward toward the black hole's central core. And what lies at that center, according to general relativity, is the singularity, a point of infinite density where all the black hole's mass is crushed into an infinitely small space. Here, the curvature of spacetime becomes infinite, the laws of physics as we know them break down completely, and our trusted equations spit out nonsensical answers. The existence of a singularity is a clear signal that Einstein's theory, for all its glory, is incomplete. It cannot handle such extremes. It screams for a deeper theory, one that can incorporate the quantum laws that must surely govern such incredible densities. For decades, this was the accepted, if unsettling, picture. A black hole was a simple, eternal, and ultimately tragic object. Things could fall in, adding to its mass and size, but nothing, not even information, could ever get out. It was a cosmic dead end. This grim fate for information was thrown into complete turmoil in 1974 when Stephen Hawking made one of the most startling theoretical discoveries of the 20th century. He applied the rules of quantum mechanics not to the black hole's interior, but to the seemingly empty space just outside its event horizon. In quantum theory, as we've seen, empty space is not truly empty. It is a seething foam of virtual particle-antiparticle pairs constantly flickering into and out of existence, borrowing energy from the vacuum before annihilating each other to pay back the debt. Hawking realized that if this quantum fluctuation happens right at the edge of the event horizon, a bizarre cosmic robbery can occur. One particle of the pair might fall across the horizon, forever lost to the black hole while its partner escapes into space. To an outside observer, it appears as if the black hole has just emitted a particle. This is Hawking radiation. The truly revolutionary consequence is that this process causes the black hole to slowly lose mass, to evaporate over astronomical timescales. A stellar mass black hole would take longer than the current age of the universe to evaporate significantly, but micro-black holes would vanish in a flash. Hawking's calculation was a monumental achievement, the first true fusion of quantum mechanics and general relativity, and it rightly made him famous. But it also created what many consider to be the most important problem in fundamental physics: the black hole information paradox. The particles that escape as Hawking radiation are completely random and thermal. they carry no information about what fell into the black hole. They are like the generic, featureless heat radiating from a warm stove. When the black hole finally evaporates completely, all that remains is this random thermal radiation. What happened to the information contained in all the things that ever fell in, the unique quantum states of every star, planet, or book that crossed the horizon? According to the bedrock principle of quantum mechanics, information can never be truly destroyed. It can be scrambled, but it must be preserved in principle. Hawking's calculation suggested it was irretrievably lost, violating a fundamental law of physics. This meant that our most basic understanding of quantum theory was wrong, a conclusion so unpalatable that Hawking himself bet against it, leading to a famous wager with other physicists. The quest to resolve this paradox has spawned some of the most creative and radical ideas in modern physics. One particularly dramatic proposal is the firewall hypothesis. It suggests that rather than being a smooth, empty space, the event horizon might actually be a blazing wall of high-energy particles, a literal firewall that would instantly incinerate anything crossing it. This would solve the information paradox by ensuring that information never actually enters the black hole. It is smeared and encoded onto the horizon itself. But this idea comes with its own huge cost. It violates the core principle of general relativity, which states that an astronaut falling through the event horizon should feel no special violent effects. You can't have both. Either general relativity is wrong at the horizon, or quantum mechanics is wrong about information. The firewall forces a brutal choice between our two most successful theories. A more elegant and increasingly favored resolution returns us to the holographic principle. Perhaps the information of everything that falls in is never actually lost behind the horizon. Instead, it is perfectly and holographically encoded on the two-dimensional surface of the event horizon itself. The three-dimensional interior is a projection of this information. In this view, Hawking radiation is not completely random and thermal. Through incredibly complex and subtle interactions, the information about what fell in is imprinted onto the escaping radiation, a process so scrambled it looks random but is, in principle, recoverable. When the black hole evaporates, the information is released back into the universe. This preserves the laws of quantum mechanics without requiring a fiery death at the horizon. Studying black holes, these darkest of objects, is thus illuminating the deepest nature of reality. It is forcing us to conceive of spacetime not as a fundamental stage, but as an emergent property of quantum information. It suggests that the universe itself might operate like a vast quantum computer, where the ultimate reality is not stuff but data. And it is at the event horizon of a black hole, this precarious ledge between the known and the unknown, that we are getting our clearest glimpse into that astonishing possibility. If the strange rules of quantum mechanics leave you questioning the nature of reality, then prepare to have your entire conception of the cosmos turned inside out and multiplied to an almost inconceivable degree. The journey to bridge the micro and macro worlds leads us to perhaps the most staggering idea in all of science, the multiverse hypothesis. This isn't just the stuff of science fiction. It's a serious, albeit speculative, consequence of trying to reconcile the mathematics of quantum theory and cosmology into a coherent whole. It proposes that our universe, with its hundreds of billions of galaxies, might be just one infinitesimal bubble in a frothing, infinite sea of universes, each with its own unique history and perhaps even its own fundamental laws of physics. This mind-expanding concept actually emerges from two distinct but potentially connected lines of thought. The first comes from the very heart of quantum mechanics itself, from an interpretation designed to solve the perplexing measurement problem. We've seen how particles exist in a blurry superposition of states until a measurement forces them to choose a definite outcome. But who or what does the measuring? And what exactly constitutes a measurement? To avoid this thorny issue, physicist Hugh Everett Roman III proposed the many worlds interpretation in 1957. In this radical view, there is no collapse of the wave function. Instead, every time a quantum system faces a probabilistic outcome, the entire universe effectively splits into multiple branches. Each possible outcome occurs, but it happens in a newly formed parallel universe. In one universe, the radioactive atom in Schrödinger's box decays and the cat dies. In another, equally real universe, the atom does not decay and the cat lives. Every quantum decision, every photon reflecting or transmitting, every electron spinning up or down constantly spawns new parallel realities. This means a version of you exists who made every different choice you ever considered, living out the consequences in a near-infinite array of alternate timelines. The second pathway to the multiverse comes from cosmology, specifically from the theory of eternal inflation we touched on earlier. If inflation, that period of hyper-expansion, can start, the mathematics suggests it may never truly stop. Instead, it becomes a self-replicating eternal process. In this picture, the fabric of spacetime is like a constantly expanding loaf of raisin bread, but where the dough itself is actively creating new raisins. Our entire observable universe is just one raisin within this infinite loaf. In other regions, far beyond our cosmic horizon, inflation continues, and in still other regions, it ends, giving rise to separate, bubble universes with their own big bangs. These bubbles are not branches of a quantum tree. They are genuinely separate regions of space-time, isolated from each other by expanding oceans of inflating space, forever beyond any possible contact. This cosmological picture dovetails powerfully with string theory, leading to the idea of the string theory landscape. For string theory to work mathematically, it requires extra dimensions of space that are curled up into tiny, complex shapes. The physics of our universe, the strength of gravity, the mass of an electron, the nature of the fundamental forces depends critically on the specific way these dimensions are folded. It turns out there is a colossal number of possible ways for these dimensions to stabilize, perhaps as many as 10 to the 500 different configurations. Each configuration corresponds to a universe with a different set of physical constants and laws. In the eternal inflationary foam, each bubble universe could represent a different point in this landscape, a random roll of the cosmic dice. In most of these universes, the constants would be wrong for the formation of atoms, stars, planets, or life. We find ourselves in a universe with the right constants, not because it's special or designed, but because it's one of the rare bubbles where conditions allowed observers like us to emerge. This is the anthropic principle applied on a cosmic scale. Physicist Max Tegmark has provided a useful framework for this dizzying proliferation of realities by categorizing multiverses into 4 levels. His level 1 multiverse is simply an extension of our own infinite space regions, so far away that they contain identical copies of you and me, simply because there are only so many ways to arrange particles in an infinite volume. Level 2 is the inflationary bubble universe model, where different bubbles may have different physical constants. Level 3 is the many worlds of quantum mechanics, where every quantum possibility is realized. Tegmark argues that levels 2 and 3 might actually be the same thing described in different languages, with quantum branching creating the new bubble universes of inflation. Then there's level 4, the ultimate ensemble, which includes all mathematically possible structures, universes governed by completely different fundamental equations, not just different constants within the same equations. The implications of this are, to put it mildly, profound. It suggests that every possible reality that can exist does exist. Somewhere, there is a universe where the dinosaurs were never wiped out by an asteroid. Somewhere, the laws of physics permit magic or allow for perpetual motion machines. The universe is not just stranger than we imagine, it is stranger than we can imagine. This idea pushes the connection between the quantum and the cosmic to its absolute limit, suggesting that the random flicker of a quantum event in the froth of the inflationary vacuum could literally give birth to an entire macro reality, complete with its own spacetime and history. Our entire cosmic story, from the Big Bang to the formation of galaxies and the evolution of life, might be just one thread in an infinite tapestry of existence, a single possibility actualized in a cosmos of limitless possibilities. But what if the most mysterious bridge between the quantum and the cosmic isn't a force or a particle, but something far more intimate, our own consciousness? This brings us to one of the most speculative, controversial, and utterly fascinating intersections in all of science: the idea that the human mind might not just observe reality, but in some way participate in its very creation. This notion stretches back to the earliest days of quantum mechanics and the famous Copenhagen interpretation, championed by figures like Niels Bohr and Werner Heisenberg. In this view, a quantum particle exists in a blurry cloud of potentialities, a wave function of probabilities until the moment it is measured or observed. It is the act of observation itself that is said to collapse this wave function, forcing the particle to choose a definite state, like a single location or a specific spin. This introduces a profound and puzzling question: what exactly qualifies as an observer? Does it require a conscious human being, a photographic plate, a cat, or simply any interaction with the larger environment? The standard physics textbook today leans heavily toward that last option, a process called decoherence, where interactions with the environment cause the quantum possibilities to rapidly decohere into a single classical outcome. Yet, the original language of the pioneers, filled with references to observation and measurement, has left a door open for a far more radical interpretation. This is where the line between established physics and philosophical speculation begins to blur. A few bold theorists, like the Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff, have proposed that consciousness isn't a mere byproduct of the brain's chemical processes, but might be a fundamental feature of the universe, rooted in quantum mechanics. Their theory, known as ORCH or orchestrated objective reduction, suggests that microtubules, tiny protein structures inside our brain's neurons, could be capable of hosting delicate quantum states. In this view, our conscious experience is the result of these quantum wave functions collapsing in a coordinated way. It's a highly controversial idea, with most physicists arguing that the warm, wet, and noisy environment of the brain would destroy any fragile quantum coherence almost instantly. While the scientific consensus remains deeply skeptical of such quantum brain biology, the theory forces a thrilling, if unproven, line of inquiry. If consciousness does have a quantum origin, however faint, then the observer is not separate from the quantum world but is deeply woven into its fabric. This leads to the ultimate, mind-bending cosmic implication. If consciousness plays a role in collapsing quantum possibilities here on Earth, could it be a fundamental property operating on a universal scale? Some interpretations of quantum mechanics, like the participatory anthropic principle proposed by physicist John Archibald Wheeler, take this idea to its grandest extreme. Wheeler suggested that we live in a participatory universe, in which observers are necessary to bring the universe into being. He used the phrase "it from bit," proposing that every particle, every field, and every force ultimately derives its existence from the answers to yes or no questions, from bits of information elicited by an act of observation. In this breathtaking vision, the universe could have remained in a nebulous, unrealized superposition of states until the first conscious observers like us evolved and looked back, retroactively solidifying a cosmic history that led to our own existence. It's a concept that feels more like metaphysics than physics, suggesting a cosmos that becomes self-aware through the life that evolves within it. It is crucial to state clearly that these ideas are far from the scientific mainstream. They reside on the outer fringes of theoretical physics, often criticized for venturing into untestable territory. The vast majority of physicists see consciousness as an emergent phenomenon of complex classical computation in the brain, not a quantum process, and view the role of the observer in quantum mechanics as a solved problem through decoherence. Yet, even as a speculative exercise, exploring this connection opens a fascinating dialogue between science and philosophy. It challenges us to consider whether mind and matter are truly separate, and whether the universe's journey from simplicity to complexity, from the first particles to conscious beings capable of wonder, might be a single, continuous, and deeply interconnected process. While we must be careful not to confuse intriguing possibility with established fact, this controversial bridge reminds us that in our quest to understand the cosmos, the greatest mystery we may ever encounter is the nature of the consciousness that is doing the seeking. While these mind-bending theories about the quantum cosmos are captivating, they would remain mere philosophical speculation without the crucial anchor of hard, empirical evidence. The true bridge between the micro and macro worlds is not built on mathematics alone. It is forged in the fires of experimentation, using some of the most sophisticated machines ever conceived by humanity. These are not abstract thought experiments. They are physical endeavors that stretch our technological limits to probe the deepest secrets of reality, seeking the tangible fingerprints of quantum processes on a cosmic scale. On the frontier of high-energy physics, our primary tool is the particle accelerator, and the crown jewel of this endeavor is the Large Hadron Collider, or LHC, buried deep beneath the border of France and Switzerland. This 27-kilometer ring of supercooled magnets is essentially a time machine. By smashing protons together at velocities incredibly close to the speed of light, it recreates, for a fleeting fraction of a second, the conditions of the universe when it was just a trillionth of a second old. Within the resulting fireball of energy, new and often exotic particles flash into existence, allowing us to test the predictions of our most fundamental theories. The most spectacular success of this method was the discovery of the Higgs boson in 2012. This was far more than just finding another particle. It was the triumphant validation of a mechanism that gives mass to everything in the universe. This process of electroweak symmetry breaking, mediated by the Higgs field, was a pivotal quantum event in the early cosmos. It is the reason why matter coalesced into the forms we see today, why stars and planets could even form. The LHC allows us to rewind the cosmic film and witness the very quantum moments that made our material universe possible, directly linking a subatomic particle to the large-scale structure of existence. But to understand the universe slightly later in its life, we must turn our gaze from the underground to the heavens using a different kind of machine, the space telescope. Missions like the Planck satellite, operated by the European Space Agency, have performed a seemingly miraculous feat. They have created exquisitely detailed maps of the oldest light in the universe, the cosmic microwave background radiation, which has been traveling for over 13 billion years. This fossilized light is not perfectly uniform. It contains tiny variations in temperature, minute hot and cold spots that are the imprint of the primordial density fluctuations from which all structure grew. The pattern of these fluctuations matches the predictions of inflationary theory with stunning precision. By analyzing this map, cosmologists can essentially read the quantum mechanical signature of the universe's infancy, seeing how those microscopic quantum jitters were stretched into the cosmic seeds for galaxies. The Planck data didn't just confirm this story. It provided the most precise measurements ever of the universe's age, composition, and geometry, all from decoding the quantum whispers frozen into the first light. Perhaps the most tantalizing prize in this cosmic treasure hunt is the search for a specific pattern in that ancient light known as B-mode polarization. This subtle swirly pattern in the polarization of the CMB is considered the smoking gun for primordial gravitational waves, the ripples in spacetime itself that were generated by the violent quantum fluctuations during the period of inflation. Detecting this signal would be direct, observational proof that gravity has a quantum nature and would provide an unprecedented window into the energy scales of the universe's first moments. While initial claims of a detection by the BICEP 2 telescope in 2014 were later attributed to interstellar dust, the hunt continues with ever more sensitive experiments. Finding this signal would be like hearing the faint echo of the Big Bang's quantum drum, a vibration that has been resonating through the expanding cosmos for all time. The quest to test these quantum cosmic links is now even extending beyond our planet. Experiments on the International Space Station, like NASA's Cold Atom Lab, are creating clouds of atoms chilled to temperatures just a billionth of a degree above absolute zero. In this state, they form a Bose-Einstein condensate, a unique quantum system where thousands of atoms behave as a single wave. Studying how these delicate quantum states behave in the microgravity of orbit allows scientists to test fundamental physics with incredible precision and explore how quantum mechanics interfaces with gravity in a way that's nearly impossible on Earth. Furthermore, plans are underway to test quantum entanglement over unprecedented distances by sending entangled photons between satellites and ground stations. Successfully demonstrating that entangled particles remain linked across thousands of kilometers would not only be a stunning technological achievement, but would also place severe constraints on theories that attempt to explain quantum weirdness through hidden mechanisms, further solidifying the non-local, interconnected nature of reality that seems to be written into the cosmos itself. But to truly bridge the gap between the quantum realm and the cosmos, we need more than just theories. We need tools of almost unimaginable precision and power. This grand quest is being driven by a new generation of technological marvels, instruments so advanced they feel like they've been pulled from the pages of science fiction. These are not just telescopes and microscopes. They are quantum sensors, gravitational wave detectors, and cosmic simulators that allow us to test our most radical ideas about the fabric of reality itself, transforming abstract mathematics into observable, tangible evidence. At the very forefront of this revolution are quantum computers, machines that leverage the bizarre principles of superposition and entanglement to perform calculations that would take classical supercomputers longer than the age of the universe to complete. Their potential for cosmology is staggering. Think about the challenge of simulating the early universe. The conditions just after the Big Bang involved an incredibly complex quantum system with a nearly infinite number of interacting particles. A classical computer simply cannot handle this complexity. It's like trying to map every grain of sand on every beach on Earth with an abacus. But a sufficiently powerful quantum computer could, in principle, simulate this primordial quantum soup by effectively becoming a quantum system itself. Researchers are already using early-stage quantum processors to run simplified simulations of quantum field theories and the dynamics of cosmic inflation, offering us a digital window into the first moments of creation. This isn't just about faster number crunching. It's about creating a new kind of laboratory where we can experiment with the universe's origins, testing multiverse hypotheses and models of quantum gravity in a virtual environment that mirrors the fundamental weirdness of reality. While quantum computers simulate the cosmos in a chip, other instruments are listening to its faintest vibrations directly. The Laser Interferometer Gravitational Wave Observatory, or LIGO, along with its partners like Virgo and Macr, has opened an entirely new sense for perceiving the universe. These are not telescopes that collect light. They are the most precise rulers ever built, designed to measure distortions in spacetime itself. Each observatory consists of two multi-kilometer-long arms arranged in an L shape. A laser beam is split and sent down each arm, bouncing off mirrors to travel back and recombine. Normally, the light waves cancel each other out, but when a gravitational wave, a ripple in spacetime caused by a cataclysmic event like two black holes merging passes through, it minutely stretches one arm while squeezing the other. This tiny change, thousands of times smaller than a proton, alters the laser light's path just enough to create a detectable signal. The first direct detection of these waves in 2015 was a monumental triumph, but the quantum-cosmic connection runs even deeper. To achieve the sensitivity required to hear these cosmic whispers, LIGO had to overcome a fundamental quantum limit, the Heisenberg uncertainty principle. The lasers themselves are so powerful that their photons, randomly bumping into the mirrors, create a quantum back-action noise that can mask the signal. To combat this, engineers are now employing squeezed light, a quantum technology that manipulates the inherent uncertainty of the photons, reducing their noise in one variable at the expense of another. This allows the detectors to peer into a quieter quantum realm, making the whispers of colliding black holes and neutron stars audible. We are literally using quantum tricks to listen to the symphony of spacetime played by massive cosmic objects, a perfect fusion of quantum engineering and gravitational astronomy. Our view of the cosmos is also being transformed by a new eye in the sky, the James Webb Space Telescope. While Hubble showed us a spectacular universe, JWST is designed to see the universe's first light. Its infrared gaze peers through cosmic dust to witness the formation of the very first stars and galaxies, illuminating the epoch of reionization when the dark ages of the universe ended. But its contribution to the quantum cosmic bridge is more profound than just pretty pictures. By studying the earliest galaxies with unprecedented detail, JWST is providing crucial data to test the predictions of how those initial quantum fluctuations from inflation evolved into the cosmic web. It is essentially fact-checking the universe's baby picture taken by the Planck satellite, verifying if the statistical patterns of galaxy formation match the quantum seeds we believe planted them. Furthermore, by analyzing the atmospheres of exoplanets, JWST-sensitive spectrographs can detect molecules like water, methane, and carbon dioxide. This search for biosignatures ties back to the anthropic principle and the fine-tuning of our universe. Finding another world with the conditions for life would provide another data point in understanding how quantum-determined constants made our existence possible. On the elusive hunt for dark matter, the tools are becoming ever more ingenious, relying on quantum phenomena to detect the undetectable. Since we only know dark matter interacts through gravity and possibly the weak nuclear force, we must build exquisitely sensitive traps. Experiments like LUX Zeppelin and Xeno NNT use massive vats of ultra-pure liquid xenon, buried deep underground to shield them from cosmic rays. When a hypothetical WIMP, a dark matter particle, passes through, it might rarely bump into a xenon nucleus, creating a tiny flash of light and a free electron. To detect this infinitesimal signal, these experiments operate at the quantum edge, using photomultiplier tubes so sensitive they can detect a single photon and electric fields to precisely measure the minute charge of a single electron. For the other leading candidate, the action, the approach is even more quantum. Experiments like ADAMS use a powerful magnet to convert a passing action into a microwave photon inside a supercooled resonant cavity. Tuning this cavity is like tuning a radio to an impossibly faint station, searching for a specific quantum note in the cosmic static. The detectors themselves are chilled to near absolute zero to exploit quantum superconductivity, reducing thermal noise to hear the faint whisper of a particle that may have been flowing through us since the beginning of time. This technological revolution is profoundly interdisciplinary. It is no longer just the realm of astronomers pointing telescopes at the sky. It is a collaborative effort that unites astrophysicists, particle physicists, quantum engineers, and computer scientists. The quest to understand the quantum cosmos is driving innovation in supercooling technologies, quantum optics, and materials science, with breakthroughs in one field rapidly benefiting others. The development of quantum sensors for fundamental physics is already finding applications in navigation, medicine, and communication. We are living in a golden age of discovery, where our tools are finally becoming sophisticated enough to interrogate the universe about its deepest secrets. Each new detection, each more precise measurement, is a stitch in the grand tapestry, weaving together the story of a cosmos born from quantum possibility and shaped into the magnificent structure we see today. This journey into the quantum cosmos does far more than just expand our scientific understanding. It fundamentally challenges the very framework through which we perceive reality, knowledge, and our place within the universe. For centuries, from the clockwork mechanics of Newton to the curved spacetime of Einstein, we built a worldview on a foundation of determinism. The idea that if we knew the position and velocity of every particle, we could, in principle, calculate the entire future and past of the cosmos. The universe was a grand, predictable movie whose every frame was predetermined by the initial conditions of the Big Bang. But quantum mechanics shatters that comforting certainty, replacing it with a core of inherent probability. The universe, at its most fundamental level, is not a story already written. It is a realm of potentialities, a tapestry of possibilities where the next moment is not certain but only statistically likely. This forces a profound philosophical shift. Are the laws of physics merely descriptions of probability? And if so, does that inject a form of genuine openness and novelty into the unfolding of cosmic history? Or is this probability just a mask for a deeper, hidden determinism we have yet to uncover, a modern echo of Einstein's insistence that God does not play dice? This confrontation between the deterministic and the probabilistic ripples directly into one of the most intimate human questions, the nature of free will. If the universe is purely deterministic, then every thought we have, every choice we make, was set in motion 13.8 billion years ago, and free will is nothing but a compelling illusion. But if the quantum world is truly probabilistic, does that actually help? A random event at the subatomic level seems like a poor foundation for what we experience as conscious, reasoned choice. We don't feel like random number generators, we feel like agents making decisions. Some philosophers and scientists, like Roger Penrose, have speculated that the answer might lie in the interface between these two worlds, that the brain might somehow harness quantum indeterminacy to generate non-algorithmic, genuinely novel thoughts. While this remains highly speculative and controversial, it illustrates how the quantum cosmic bridge forces us to re-examine the most basic aspects of our human experience, blurring the line between the physics of the external world and the metaphysics of the mind. Our concepts of time and causality, those bedrock principles of our existence, are also turned inside out when we cross this bridge. In our macroscopic world, time flows inexorably forward in a clear chain of cause and effect. A billiard ball moves because another one struck it, but in the quantum realm and in its cosmological applications, this tidy sequence breaks down. Quantum entanglement presents us with spooky correlations that appear to defy local causality, with particles influencing each other instantly across vast distances. The transactional interpretation of quantum mechanics even allows for influences that travel backward in time. In the realm of cosmology, the arrow of time itself becomes a puzzle. Why does time move forward? The most compelling answer comes from the second law of thermodynamics and the increase of entropy. The universe moving from a state of low entropy at the Big Bang to a state of high entropy in the future. But this just pushes the question back a step. Why did the universe begin in such a spectacularly low entropy, ordered state? Some, like Sean Carroll, suggest the answer might lie in the larger multiverse landscape, where our universe is just one region with a favorable arrow of time. This means the flow of time may not be a fundamental property of the universe, but an emergent one, a contingent feature of our particular cosmic neighborhood. This challenges the philosophical ideas of Immanuel Kant, who argued that time and space are not things we discover in the world, but are the fundamental categories of our human perception, the necessary lenses through which we experience reality. The quantum cosmos suggests that Kant was both right and wrong. He was right that our classical perception of a smooth, continuous spacetime is a kind of user interface our brains construct to navigate the world. But he was likely wrong that this interface reflects the true, fundamental nature of reality. The real world at the Planck scale might be granular, non-local, and not even possess a single objective direction of time. Our perception is a useful illusion, a low-resolution approximation that breaks down when we probe too deeply. This means that science is not just a process of discovering what's out there. It is also a process of discovering the limits of our own innate cognition, of learning to see past the illusions our own minds create. Ultimately, this entire endeavor pushes against the limits of science itself. The scientific method is built on observation, measurement, and repeatability. But what happens when we try to observe the thing that may have created the conditions for observation itself, like the inflationary multiverse? What happens when the act of measurement fundamentally alters the system, as in quantum mechanics? We are forced to confront the possibility that there may be aspects of reality that are, in principle, unobservable to us, forever beyond the reach of empirical verification. This doesn't mean we should stop inquiring, but it does invite a certain humility. The quest to bridge the quantum and the cosmic is more than a technical puzzle. It is a fundamental part of the human journey to understand our own existence. It asks not only how the universe works, but why there is a universe at all, and what it means that we, a collection of stardust animated by quantum processes, have evolved the consciousness to even ask these questions. The equations of physics describe the mechanisms, but the philosophical implications touch upon the meaning, connecting the dance of particles to the profound human experience of wonder, awe, and the relentless pursuit of truth in a vast and mysterious cosmos. Standing on the shoulders of these monumental discoveries, we now look out toward the horizon, to the next great leaps that promise to reshape our understanding of the quantum cosmos. The journey is far from over. In many ways, it is accelerating into a future brimming with breathtaking possibilities. The coming decades will be defined by a new generation of instruments, both on Earth and in space, designed with one audacious goal in mind: to finally witness the direct signatures of quantum gravity and to hear the faint echoes of other universes. This isn't just about building bigger versions of what we have. It's about pioneering entirely new ways of observing reality, pushing the boundaries of technology to where the laws of physics as we know them begin to blur and warp. The quest to listen to the ripples in space-time is about to get a massive upgrade. While LIGO and Virgo have given us the gift of gravitational wave astronomy, their current design is limited to hearing the high-frequency crashes of stellar mass black holes and neutron stars. To tune into the lower frequency hum of the cosmos, the mergers of supermassive black holes at the hearts of galaxies, or even the primordial gravitational waves from inflation itself, we need a much more sensitive ear. This is the driving vision behind the Einstein telescope, a proposed underground observatory with arms 10 kilometers long, arranged in a triangular configuration. By being buried deep beneath the surface and using cryogenically cooled components, this next-generation detector will be so incredibly quiet that it could hear gravitational waves 1,000 times fainter than what LIGO can detect today. It would allow us to peer back to the very first seconds after the Big Bang, potentially capturing the vibration from cosmic inflation, the holy grail of evidence that would directly connect the quantum foam to the cosmic structure we see today. Alongside it, the Laser Interferometer Space Antenna, or LISA, a planned space-based constellation of 3 spacecraft flying in formation millions of kilometers apart, will open up a completely new gravitational wave frequency band, free from the seismic noise of Earth, listening to the symphony of the universe from the quiet of space. On the particle physics front, the ambition is just as staggering. The Large Hadron Collider was a triumph, but it has likely reached the limits of what it can teach us about the quantum origin of the cosmos. The conversation has now turned to the Future Circular Collider, a proposed machine with a circumference of over 90 kilometers, more than 3 times the size of the LHC. Its primary mission would be to study the Higgs boson with unimaginable precision, essentially using it as a microscope to probe the universe at energies a full order of magnitude higher. This could reveal whether the Higgs field is truly elementary or if it's made of smaller constituents, and it could uncover new, hidden symmetries of nature or even evidence of extra dimensions. The data from such a machine would provide crucial stress tests for our current theories and could offer the first experimental clues toward a theory of quantum gravity by revealing how particles behave at energies that approach the Planck scale. Theoretical physics is not standing still, waiting for these experiments to be built. The landscape of ideas is evolving at a furious pace. In string theory, researchers are moving beyond the initial mapping of the vast landscape of possible universes and are now focusing on the swampland, the set of seemingly consistent effective field theories that are actually incompatible with a full theory of quantum gravity. This effort aims to derive concrete, testable criteria that any viable theory must meet, potentially allowing us to use cosmological observations to rule out large swaths of the string theory landscape. Simultaneously, other approaches like causal set theory and asymptotic safety in quantum gravity are gaining traction, offering alternative, minimalist visions where spacetime emerges from a network of discrete events or where gravity becomes predictable at high energies without needing extra dimensions. The goal is no longer just mathematical consistency. It is to produce clear, falsifiable predictions about what we should see in the cosmos, turning philosophy into physics. Perhaps the most tantalizing frontier is the direct detection of the dark universe, the next decade could finally answer the century-old question, what is dark matter? Ultra-sensitive experiments like LZ and its successors will continue to hunt for WIMP, pushing sensitivities to the point where they will either find them or rule out the concept entirely. The search for actions is entering a golden age, with experiments like ADMX and Haystack becoming increasingly sophisticated, tuning through the possible mass range of these elusive particles with quantum precision. A confirmed detection would not only solve the dark matter puzzle, but would also represent the discovery of an entirely new type of fundamental particle, opening a window into physics far beyond the standard model. And for dark energy, the recently launched Euclid Space Telescope and the Vera-C, Rubin Observatory will create the most detailed 3D maps of the universe's expansion history ever made, measuring the influence of dark energy over 10 billion years with exquisite detail. This could tell us if dark energy is truly a constant cosmological constant, or if it varies over time, a discovery that would completely upend our current models of cosmic evolution. Underpinning all these efforts is a new spirit of global, interdisciplinary collaboration. The scale of these projects, from the billion-dollar price tag of a new collider to the international consortia required to build a telescope like the Einstein telescope, means that no single nation can do it alone. Physicists, astronomers, engineers, and computer scientists are working together as never before, sharing data and insights across traditional boundaries. The field of quantum cosmology is becoming a grand, collective human endeavor, a testament to our shared curiosity about the universe. This collaborative spirit is our greatest asset, pooling the world's intellectual and technological resources to tackle problems that have persisted for a century. The path forward is lit by the promise that the gap between the quantum and the cosmic is not a permanent divide, but a frontier waiting to be crossed. With each new experiment and each theoretical breakthrough, we move closer to a revolutionary new cosmic narrative, one that will seamlessly weave together the story of the smallest particles with the grandest scales of the universe, revealing a reality more interconnected and magnificent than we have ever dared to imagine. If this journey into the quantum cosmos has ignited a spark of curiosity, the wonderful news is that you don't need a PhD or a particle accelerator to continue the exploration. The adventure is just beginning, and there is a wealth of incredible resources available to guide your learning, from beautifully written books to immersive online courses and captivating documentaries. For those who want to build a solid foundation, a few standout books serve as perfect launchpads. Brian Cox and Jeff Forshaw's The Quantum Universe does a phenomenal job of demystifying quantum mechanics without oversimplifying it, walking you through the concepts with clarity and a genuine sense of wonder. To understand how these ideas stitch together the fabric of reality, there's no better guide than Brian Greene's The Fabric of the Cosmos, which masterfully navigates the worlds of spacetime, relativity, and quantum theory, making the most profound ideas feel within reach. For learners who thrive in a more structured environment, the digital age has opened up universities to everyone with an internet connection. Platforms like Coursera and edX host excellent courses from world-class institutions. You can find introductory courses on astronomy and cosmology that will give you the big picture, or you can dive deep into specialized topics like particle physics or general relativity, often taught by leading professors in the field. These courses allow you to learn at your own pace, with video lectures, quizzes, and forums to connect with fellow students from around the globe, turning a solitary pursuit into a shared experience. Sometimes the most powerful way to grasp these vast concepts is to see them brought to life. Documentaries remain an unparalleled medium for making the cosmos feel tangible. The classic PBS Nova series, especially episodes like The Fabric of the Cosmos based on Green's book, use state-of-the-art graphics and thought-provoking experiments to visualize the invisible. For a more sweeping narrative, the reboot of Carl Sagan's Cosmos, hosted by Neil deGrasse Tyson, beautifully connects the story of the universe to the human quest for knowledge, inspiring a sense of awe that is both humbling and empowering. If you're looking for content to accompany your daily commute or workout, the world of podcasts offers a constant stream of insight. Shows like Star Talk Radio blend science, pop culture, and humor to explore big questions in an accessible way, while more technical podcasts like The Quantum Times or interviews on the Sean Carroll podcast delve into the nuances of current research and debates with leading physicists. These audio experiences let you eavesdrop on the conversations happening at the very frontier of knowledge. Perhaps the most rewarding step you can take is to connect with the vibrant community of enthusiasts and experts who share your fascination. Online forums like the Physics subreddit or specific groups on platforms like Discord and Facebook are filled with people of all knowledge levels, from curious beginners to professional researchers, all discussing the latest news, answering questions, and debating interpretations. Don't be afraid to lurk, read, and eventually participate. These communities are built on a shared passion for understanding the universe, and your perspective is a valuable addition. The journey into the quantum cosmos is not a path walked alone. It's a collective human endeavor, and your curiosity is the most important tool you bring. Now, as we navigate these astonishing ideas connecting the quantum realm to the cosmos, it's crucial that we pause and clear away some of the common misconceptions that often cloud the public's understanding. Popular culture and oversimplified explanations have, unfortunately, created a mythology around these topics that can be more confusing than enlightening. Let's start with one of the biggest and most persistent myths about quantum mechanics, the idea that it means everything is fundamentally random and uncertain. While it's true that quantum physics deals in probabilities, this is often misinterpreted as pure, chaotic randomness. In reality, these probabilities are governed by precise, deterministic mathematical equations, the Schrödinger equation, that predict the likelihood of various outcomes with incredible accuracy. The universe isn't rolling dice in a dark room. It's more like following a complex but perfectly defined recipe where the exact outcome isn't predetermined, but the range of possible outcomes is strictly bound by the laws of physics. This isn't randomness in the everyday sense of the word. It's a deeply structured probabilistic nature that, on average, leads to the stable, predictable world we see around us. This leads us directly to the most famous feline in all of science, Schrödinger's cat. This thought experiment is constantly referenced, but its true purpose is almost always lost. Schrödinger did not create this scenario to suggest that cats can be both dead and alive. In fact, he devised it as a kind of reductio ad absurdum to highlight what he saw as the sheer ridiculousness of applying quantum superposition directly to everyday objects. The cat was meant to be an illustration of a paradox, not a description of reality. In the decades since, physicists have developed a solid understanding of a process called decoherence, which explains why we never see superposition at our scale. A macroscopic object like a cat is constantly buffeted by its environment, colliding with air molecules, being touched by light, and interacting in trillions of ways every second. These countless interactions continuously measure the system, forcing it to collapse from a blurry quantum state into a single, definite classical reality almost instantly. The cat is never in a true blended state. The thought experiment simply serves to show where our intuitive, classical world diverges from the quantum reality beneath it. Another widespread myth is that this quantum weirdness suggests the universe is some kind of illusion, or that nothing is truly real. This often gets tangled up with misinterpretations of the holographic principle. While it's true that some theories propose that our three-dimensional reality could be a projection of information stored on a two-dimensional boundary, this does not mean the universe is an illusion in the philosophical sense. The tables we bump into, the stars we see in the sky, and the ground beneath our feet are all very real in terms of their physical effects and our experience of them. The discovery of a deeper, more fundamental description of reality doesn't make our experienced reality any less valid. It simply means that the underlying code of the universe is far stranger and more wonderful than we previously imagined. It's the difference between saying a video game is an illusion and understanding that it is run on a computer's hardware and software. The game is still a real, interactive experience, even if it emerges from a layer of binary code. Shifting our gaze to the cosmos, black holes are perpetually shrouded in misconception. The name itself is part of the problem. Calling them holes implies an empty void, a nothingness. Nothing could be further from the truth. A black hole is not an empty hole in space. It is an immense amount of matter compressed into an infinitesimally small point of infinite density, a singularity surrounded by an invisible boundary called the event horizon. It is the most extreme concentration of mass and energy possible, warping spacetime so severely that within a certain radius, the escape velocity exceeds the speed of light. They are not cosmic vacuum cleaners indiscriminately sucking everything in. Their gravitational pull is just like that of any other object of the same mass. If our sun were magically replaced by a black hole of the same mass, all the planets would continue orbiting in their exact same paths, completely unharmed, though rather cold and dark. The terror and mystery of black holes come from their extreme physics, not from them being celestial drains. Finally, we have the mysteries of dark matter and dark energy, which are often conflated or misunderstood. A common error is the belief that dark matter is some kind of anti-gravity force. This is not the case. Dark matter behaves exactly like regular matter in one key aspect. It exerts attractive, regular gravity. We detect it because its gravitational pull influences the motion of stars within galaxies and the bending of light from distant objects. It's called dark because it doesn't interact with light or any other part of the electromagnetic spectrum. It is completely invisible and transparent, not because it has repulsive properties. Dark energy, on the other hand, is the true source of the repulsive effect driving the accelerated expansion of the universe. But it is not a force in the traditional sense. It is a property of space itself, a constant energy density permeating the vacuum. Thinking of dark matter as the invisible scaffolding that holds galaxies together through gravity, and dark energy as the mysterious pressure stretching the very fabric of the cosmos, helps keep these two very different concepts distinct. By dispelling these myths, we can move past the sensationalism and appreciate the true, awe-inspiring nature of these discoveries, which are wondrous enough on their own without needing any extra layers of misunderstanding. As we venture deeper into the connections between the quantum realm and the cosmos, we encounter a concept that is as profound as it is controversial, one that directly addresses the most haunting question of all: why does our universe seem so perfectly tailored for our existence? This is the anthropic principle, the idea that the fundamental constants and laws of nature appear to be exquisitely fine-tuned to allow for the emergence of life. Consider the force of gravity, for instance. If it were even slightly stronger, stars would burn their fuel too rapidly and collapse into black holes before life could evolve. If it were marginally weaker, matter would never have coalesced into stars and galaxies at all. The strength of the strong nuclear force is equally precarious. A tiny change would prevent the formation of carbon, the essential element for life as we know it. The cosmological constant, which governs the acceleration of the universe's expansion, is fine-tuned to an astonishing precision of 1 part in 10 to the power of 120. A value any larger would have blown the universe apart before atoms could form. Any smaller would have caused it to recollapse instantly. This incredible precision is not just a single lucky break. It is a long chain of cosmic coincidences, a series of constants and forces that all had to be set to just the right values to make our existence possible. This staggering fine-tuning naturally leads to a monumental question. Is this apparent perfection a sign of deliberate design, or is there a scientific explanation that can account for it? This is where the quantum world and the concept of the multiverse collide in a fascinating proposal. The initial conditions of our universe, including the values of these fundamental constants, were likely set during the universe's first moments, a period dominated by chaotic quantum fluctuations. In this view, the constants are not predetermined by some grand equation, but are the result of a random quantum lottery. Most of the possible values for these constants would lead to dead, sterile universes. But if there are a vast number of universes, a multiverse, each with its own randomly selected set of physical laws spawned from quantum possibilities, then it is no surprise that we find ourselves in one of the rare habitable ones. We could not possibly observe a universe that was not fine-tuned for our existence. The quantum randomness that seeded our galaxies also, in this framework, provides a potential answer to the riddle of fine-tuning, transforming it from a miraculous accident into a statistical inevitability within a vast cosmic ensemble. Within this broad idea, philosophers and scientists distinguish between two main versions of the anthropic principle. The weak anthropic principle is a relatively modest and widely accepted statement. It simply notes that we must be prepared to take into account the fact that our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. We observe a universe that is old enough for elements like carbon to have been forged in stars, and a planet orbiting at just the right distance from a stable star, because we couldn't be here to observe otherwise. It is a statement about selection effects in observation. The strong anthropic principle, however, makes a much bolder claim. It suggests that the universe must have those properties which allow life to develop within it at some stage in its history. This version often veers into more metaphysical territory, sometimes interpreted to imply that the laws of nature are in some sense compelled to allow for the emergence of consciousness, a viewpoint that makes many physicists deeply uncomfortable as it borders on teleology, the idea that nature has a purpose or goal. The debate over the anthropic principle often centers on whether it is a legitimate scientific explanation or a philosophical cop-out. Critics argue that invoking a multiverse to explain fine-tuning is ultimately untestable and non-falsifiable. If we cannot interact with or observe these other universes, they say, then the idea is more akin to metaphysics than physics, a clever way to explain away a problem without providing any concrete evidence. Proponents counter that the anthropic principle is a necessary tool for cosmology. When a theory predicts a multiverse of possibilities, the fact that we observe one specific outcome is a crucial piece of data that must be used to test the theory. They point to the cosmological constant problem as a prime example. The observed value of the constant is vastly smaller than what particle physics predicts. The multiverse and anthropic reasoning offer a potential solution. While most universes have a large cosmological constant, we naturally reside in one of the extremely rare ones where it is small enough to allow galaxies to form. This approach provides a statistical framework for understanding why our universe looks the way it does, even if it challenges our traditional notions of scientific verification. Ultimately, the anthropic principle forces us to confront our place in the cosmos on a truly cosmic scale. It ties the quantum randomness at the birth of the universe directly to the conditions that allowed for galaxies, stars, planets, and life. It suggests that our existence is both incredibly special and, in a vast multiverse, statistically inevitable. Whether one views it as a profound scientific insight or a philosophical stopgap, it undeniably expands our perspective, humbling us with the possibility that our entire universe is just one bubble in an infinite froth of reality, while simultaneously empowering us with the realization that we are the part of the cosmos that has become aware of itself, capable of pondering its own origins, its seemingly fine-tuned laws. Yet if we think of time as a river flowing in one direction, the quantum realm presents us with a bewildering counterpoint, a reality where the very concept of a universal, flowing time begins to break down into something far more fluid and mysterious. This brings us to one of the most profound and perplexing puzzles in all of physics, the problem of time itself, and how its nature changes drastically as we cross the bridge from the quantum world to the cosmic stage. In our everyday lives, time seems simple enough. It's the steady, relentless tick of a clock, the irreversible process of aging, the clear distinction between a remembered past and an uncertain future. This intuitive arrow of time is deeply woven into our experience of reality. But when we descend to the quantum scale, this comfortable notion begins to dissolve. In the standard equations of quantum mechanics, time isn't treated as something that emerges from more fundamental parts. It is an external parameter, a fixed background stage against which the quantum drama unfolds. The Schrödinger equation, which describes how quantum states evolve, treats time as a smooth, continuous, and universal conductor, directing the evolution of probability waves without being affected by them. In this picture, time is absolute and external, much like it was in Newton's classical physics. But then we shift our perspective to the grand cosmos, described by Einstein's theory of general relativity, and time undergoes a radical transformation. Here, time is no longer a rigid external backdrop. It is dynamic and plastic, woven together with the three dimensions of space into a single, flexible fabric called spacetime. The presence of matter and energy curves this spacetime, and this curvature tells objects how to move. Crucially, this also means that time itself can be warped. It flows at different rates depending on gravity and velocity. A clock at the top of a mountain ticks ever so slightly faster than a clock at sea level, and an astronaut orbiting the Earth ages a tiny fraction of a second slower than their twin on the ground. In relativity, time is relative and dynamical, a player in the cosmic game rather than just the referee. This creates a fundamental clash when we try to merge these two theories into a single theory of quantum gravity. Quantum mechanics needs a fixed, external time to define its evolution, but general relativity says no such thing exists. Time is part of the dynamical field that must be quantized. This is the essence of the problem of time, a central obstacle that has stumped physicists for decades. How do you describe the evolution of a quantum system when the very clock you would use to measure that evolution is itself a quantum variable, subject to fluctuations and uncertainty? One radical approach to solving this problem is to suggest that time isn't fundamental at all, but an emergent property that arises from a more basic, timeless reality underlying the universe. This is the idea behind the timeless wave function of the universe, proposed by physicists like Bryce DeWitt and James Hartle. In their formulation, the entire universe is described by a single, stationary wave function that doesn't evolve in time, but instead encompasses all of reality at once. In this picture, the past, present, and future are all equally real, frozen in a single mathematical structure. Our perception of time flowing, of one moment succeeding another, would then be a kind of illusion, a perspective that emerges from within this timeless whole because of the way we, as complex organisms within the universe, process information and interact with the world. It's akin to looking at a single frame of a movie film that contains the entire story. The flow isn't in the film itself, but in our experience of projecting it. Other approaches seek to define time internally through relationships between physical events. The idea of a quantum clock suggests that time could be measured by the evolution of one part of a quantum system relative to another, rather than against some external standard. For instance, the spin of one particle could serve as a clock for the position of another, but these internal clocks are themselves quantum objects, subject to the uncertainty principle, meaning that time itself would become fuzzy and uncertain at the fundamental Planck scale. There would be a fundamental limit to how precisely we can measure intervals of time, suggesting that the smooth, continuous flow we experience is actually a coarse-grained approximation of a discrete, jittery underlying reality. Now, let's scale this quantum notion of time up to the very beginning of everything. The standard cosmic timeline begins with the Big Bang, a moment where our current laws of physics break down in a singularity of infinite density. But if we apply these quantum gravity ideas, a fascinating alternative emerges. Perhaps there was no beginning. In approaches like loop quantum cosmology, the Big Bang singularity is replaced by a big bounce, where a previous contracting universe reached a maximum density, and then quantum gravitational repulsion caused it to rebound into our expanding universe. In this view, time extends backwards indefinitely, and the singularity is merely a bridge between cosmic epochs. The very earliest moments of our universe, from time 0 to the Planck time 10 to the negative 43 seconds, are known as the Planck epoch. During this unimaginably brief interval, the energy and density were so extreme that all four fundamental forces of nature were likely unified into a single superforce, and the concepts of space and time as we know them ceased to have any meaning. It was a realm of pure quantum foam where spacetime itself fluctuated wildly. Our classical arrow of time, the one that points from the ordered past to the disordered future, may have its origin in the specific initial conditions set during this quantum genesis. The universe was born in a state of incredibly low entropy, a state of exquisite order, and the second law of thermodynamics dictates that entropy must increase over time, creating the irreversible arrow we experience. But why was the initial entropy so low? This remains one of the deepest unanswered questions, and the answer may lie in the quantum boundary conditions of the universe itself, a timeless wave function that selected a highly ordered state from the quantum possibilities. This journey through quantum time reveals that our familiar, flowing time is likely not a fundamental feature of the cosmos, but a robust emergent property that arises from the collective behavior of countless quantum processes. The smooth, universal tempo we experience in our daily lives is like the calm surface of an ocean, hiding a turbulent, probabilistic depth where time loses its meaning. Understanding this quantum nature of time isn't just an academic exercise. It holds the key to resolving the greatest cosmic mysteries, from the initial singularity of the Big Bang to the ultimate fate of the universe. It suggests that to truly grasp the beginning of everything, we must let go of our classical intuition of a starting clock and embrace a reality where time itself is born from the timeless dance of quantum possibilities. If you could peer into the depths of what appears to be utterly empty space, you would witness a scene of unimaginable chaos and creativity. The quantum vacuum is not a void of nothingness. It is a seething, bubbling sea of potentiality, a foam of existence where the very concepts of something and nothing lose their meaning. This frenzy of activity is a direct consequence of Heisenberg's uncertainty principle, which we've met before. It tells us that we can never precisely know both the energy of a system and the exact time for which that energy exists. This inherent fuzziness allows for a breathtaking loophole in the conservation of energy, but only for the briefest of moments. Particles and their antimatter counterparts can spontaneously blink into existence, borrowing energy from the vacuum before annihilating each other and vanishing back into the void, repaying their energy debt almost instantly. These are virtual particles, and their fleeting existence is the reason we now understand that the vacuum of space is not passive or empty, but is instead the most active and energetic thing imaginable. This ceaseless creation and destruction isn't just a theoretical curiosity. It produces a tangible, measurable energy that permeates every cubic centimeter of the cosmos. This is the zero-point energy, the lowest possible energy that a quantum mechanical system may have. Unlike classical physics, where a system can reach absolute zero and have zero energy, a quantum system always retains this residual, jittering energy. It's as if the universe can never truly sit still, even at its coldest and most quietest state. This zero-point energy of the quantum vacuum has a profound and, frankly, perplexing implication for cosmology. According to the principles of quantum field theory, this energy should act as a sort of background hum of the universe, and according to Einstein's general relativity, all energy gravitates. This vacuum energy would have a repulsive gravitational effect, a kind of anti-gravity that pushes space itself apart. This sounds remarkably like the observed effect of dark energy, the mysterious force driving the accelerated expansion of the universe. It seems like a perfect fit, an elegant solution to one of cosmology's greatest mysteries, but here we encounter the most staggering numerical discrepancy in all of science. When physicists attempt to calculate the theoretical value of this quantum vacuum energy, the result is a number so astronomically large it defies comprehension. The calculation suggests an energy density that would be 1 followed by 120 zeros larger than the value we actually observe from measuring the rate of the universe's expansion. This is not a small error. It is a catastrophic failure of our theories to align with reality. A universe with that much vacuum energy would have been torn apart in the first instance of the Big Bang, never allowing a single atom, let alone a galaxy or a planet, to form. This colossal problem is known as the cosmological constant problem, and it represents a glaring rift between our understanding of the quantum world and the cosmic realm. It is a clear signal that we are missing a crucial piece of physics, perhaps a symmetry that cancels out this energy, or a revolutionary new understanding of how gravity works at the quantum scale. One of the most beautiful and convincing demonstrations that this quantum foam is real comes not from looking at the stars, but from a delicate laboratory experiment here on Earth, the Casimir effect. Imagine two uncharged, perfectly smooth metal plates placed incredibly close together in a vacuum, separated by a tiny gap mere nanometers wide. In the vast space outside the plates, a rich spectrum of virtual particles of all wavelengths can flicker in and out of existence. However, in the narrow gap between the plates, only virtual particles with wavelengths that fit perfectly between them can appear, like notes on a guitar string that can only vibrate at certain frequencies. This means there are slightly more virtual particles exerting pressure on the outside of the plates than on the inside. The result is a tiny but measurable force that pushes the plates together. This is not some theoretical prediction. The Casimir effect has been experimentally verified repeatedly. It is direct, incontrovertible proof that the quantum vacuum is real and that these virtual particles have tangible physical effects, providing a tiny, microscopic push that confirms one of the strangest predictions of quantum theory. This breathtaking concept, that particles can emerge from nothing, naturally leads to the most profound question of all. Could our entire universe be the result of a quantum fluctuation on the grandest possible scale? Could the ultimate something have come from the ultimate nothing? This idea moves from the solid ground of verified physics to the speculative frontier of cosmology, but it is a frontier explored by serious physicists. The key lies in the total energy of the universe. When we account for all the positive energy contained in matter and radiation, and the negative energy stored in the gravitational field, some calculations suggest the sum total could be exactly zero. If that is true, then the universe is the ultimate free lunch. It could have spontaneously emerged from the quantum vacuum, a fluctuation that didn't need to borrow any net energy because its total energy balanced perfectly to zero. In this scenario, the Big Bang wasn't an explosion in space and time, but the sudden appearance of space and time from a primordial quantum event. This doesn't require a creator or an external cause. It requires only the bizarre but well-established rules of quantum mechanics operating on a cosmic canvas. While this remains a highly speculative and philosophically charged idea, it underscores a revolutionary shift in our understanding. Empty space is not empty. It is a generative medium, a fertile ground from which particles, forces, and perhaps even entire universes can spontaneously arise, forever blurring the line between the quiet void and the vibrant cosmos we call home. At the heart of physics lies a powerful and beautiful idea that has become our most reliable guide in the quest to understand the universe, from the smallest particles to the largest cosmic structures, the concept of symmetry. This isn't just about the pleasing, balanced shapes of a snowflake or a butterfly's wings. In physics, symmetry refers to something much deeper, an invariance, a property that remains unchanged even when we perform a transformation on the system. If you can rotate an object, flip it, or move it through time and space and its fundamental properties stay the same, then that object possesses a symmetry. This simple principle has proven to be the most powerful engine for discovery in modern physics, acting as a cosmic signpost pointing toward the fundamental laws that govern everything. The true power of symmetry reveals itself in the quantum realm through what are known as gauge symmetries. These are not symmetries of objects, but symmetries of the underlying quantum fields themselves, the fundamental entities that make up our reality. Imagine a field that represents an electron. A gauge symmetry means that we can change how we describe that field at every point in space in a specific, mathematical way, like shifting the phase of its quantum wave. And yet, all the observable physics, all the forces and interactions remain completely unchanged. This requirement that the laws of physics must be invariant under these local transformations isn't just a mathematical curiosity. It actually forces the existence of the fundamental forces themselves. For the U1 gauge symmetry of electromagnetism, this requirement necessarily gives rise to the photon, the carrier of the electromagnetic force. The symmetry dictates that the field must interact in a specific way, and that interaction is what we experience as a force. This profound insight forms the core of the standard model of particle physics. The strong and weak nuclear forces also emerge from their own specific gauge symmetries, SU3 and SU2 respectively. In this breathtakingly elegant framework, the forces of nature aren't just happenstance. They are the inevitable consequences of the universe's demand for local symmetry. However, a universe with perfect, unbroken symmetry would be a very different and far less interesting place. If all the symmetries of the standard model remained intact, particles like electrons and quarks would be massless, zipping around at the speed of light, never clumping together to form atoms, molecules, or people. This is where one of the most important processes in the cosmos comes into play: spontaneous symmetry breaking. This is the idea that the laws of physics possess a symmetry, but the ground state or vacuum of the universe does not. A classic, everyday example is the formation of a crystal. The laws of fluid dynamics that govern liquid water are perfectly symmetric. They are the same in every direction. But when water freezes into ice, the water molecules must choose specific positions to form a crystal lattice. The symmetry of the liquid is broken. The system has settled into a lowest energy state that is no longer perfectly symmetric. The laws still possess the symmetry, but the system's chosen state does not. In the early universe, a cosmic version of this freezing process occurred, and it is responsible for your very existence. This is the Higgs mechanism. In the searing heat just after the Big Bang, the Higgs field, which is associated with a particular symmetry, had a value of 0 everywhere. The universe was symmetric and all fundamental particles were massless. But as the universe expanded and cooled, it underwent a phase transition, much like water freezing into ice. The Higgs field settled into a new, non-zero ground state everywhere in space. This broke the symmetry. The consequence is that now, as other particles move through this ubiquitous Higgs field, they interact with it. This interaction is what we perceive as mass. Some particles, like photons, don't interact with it at all and remain massless. Others, like electrons and quarks, interact strongly and gain significant mass. The Higgs mechanism is the reason matter has substance, the reason atoms can form, and the reason the complex structures of our universe could ever emerge from a hot, symmetric beginning. This dance of symmetry and its breaking is not confined to the quantum world. It is written across the largest scales of the cosmos. When we look out into the universe, we observe a high degree of isotropy and homogeneity. The cosmos looks roughly the same in every direction, and on the largest scales, the distribution of matter is smooth. This is a profound cosmic symmetry, yet this symmetry is also broken. If it were perfect, the universe would be an utterly uniform, featureless soup of particles. Instead, we see a magnificent cosmic web of galaxies and vast voids. This large-scale structure is the result of the gravitational amplification of tiny primordial density fluctuations. And where did those initial fluctuations come from? They are thought to be the quantum fluctuations of the inflatoned field, the driver of cosmic inflation, frozen into the fabric of the universe when inflation ended. The end of inflation itself was likely a spectacular episode of symmetry breaking, a phase transition that released a colossal amount of energy that reheated the universe and set the stage for the Big Bang as we know it. The very formation of galaxies, stars, and planets can be seen as a cascade of symmetry-breaking events, starting from quantum seeds and evolving through gravity into the structured universe we observe today. This deep connection reveals a stunning unity in the laws of physics. The same mathematical principles that explain why a photon is massless and how crystals form also govern the evolution of the entire cosmos. Symmetry provides a universal language that bridges the gap between the quantum and the cosmic. It shows us that the elegance and order we perceive in the physical world are not accidents but the direct result of fundamental invariances woven into the fabric of reality. From the forces that bind atoms to the galaxies that spin in the void, the universe is a tapestry of symmetry, both preserved and broken, telling a story of how simplicity at the most fundamental level gives rise to the incredible complexity and beauty we see at every scale. But what if the universe is not made of stuff at all? What if the fundamental ingredient of reality isn't matter or energy, but something far more abstract and powerful: information itself? This is the radical proposition at the heart of quantum information theory, a field that reframes our entire understanding of physics by treating information not as an abstract concept, but as a tangible, physical quantity. In this view, the universe isn't a collection of swirling particles in empty space. It's a cosmic computer of unimaginable complexity, processing the laws of physics through the manipulation of quantum bits. At the core of this idea is the qubit, the fundamental unit of quantum information. Unlike a classical computer bit, which can only be a 0 or a 1, a qubit exists in a superposition of both states simultaneously. It's this inherent fuzziness and potential that gives quantum information its incredible power, allowing for a density and richness of processing that no classical system could ever achieve. This quantum information isn't just stored statically, it's constantly interacting, flowing, and becoming entangled. A key measure of this activity is something called entanglement entropy, which quantifies how much information is shared between different parts of a quantum system. When two particles become entangled, their information becomes inextricably linked, and the entanglement entropy between them increases. This isn't just a theoretical curiosity. It appears to be a fundamental feature of how the universe organizes itself. The vacuum of empty space itself is teeming with entanglement between different regions, creating a complex web of quantum connections that might be the very glue holding spacetime together. The more we look, the more it seems that entanglement isn't just a bizarre property of particles. It's the foundational language of the cosmos, the way the universe stores and processes data about itself. Nowhere is this more dramatically illustrated than in the physics of black holes. These cosmic anomalies have forced us to completely rethink the relationship between information, gravity, and reality. As we've discussed, the black hole information paradox presents a terrifying puzzle. What happens to the information that falls into a black hole when the black hole itself eventually evaporates through Hawking radiation? Quantum mechanics insists that information can never be destroyed, but general relativity seemed to suggest it was lost forever in the singularity. The resolution emerging from the holographic principle is that black holes might be the ultimate information processors. The information about everything that ever fell in isn't stored in the mysterious interior. It is perfectly and holographically encoded on the two-dimensional surface of the event horizon. The three-dimensional black hole we picture is a projection of this two-dimensional data. When Hawking radiation is emitted, this information is not lost but is slowly and meticulously radiated back out into the universe in a scrambled but recoverable form. A black hole, then, is not a cosmic trash compactor. It is nature's most extreme and efficient quantum hard drive, pushing the limits of how much information can be stored in a given volume of space. This leads to a staggering and profound idea. If black holes are information processors, could the entire universe be one as well? The concept known as it from qubit suggests exactly that. The proposal is that the universe fundamentally computes its own evolution. The motion of planets, the fusion inside stars, the formation of galaxies, all of it could be the output of a continuous, pervasive quantum computation. The laws of physics, from gravity to electromagnetism, wouldn't be primary. They would be the emergent software that runs on the universe's underlying quantum computational hardware. In this picture, the smooth, continuous spacetime of general relativity is an illusion that emerges from a vast network of discrete, interacting quantum bits. The depth and geometry we experience are not fundamental. but are generated by the complex patterns of entanglement between these fundamental informational building blocks. We are not living in a universe that has information. We are living inside a universe that is information, a cosmic data structure constantly updating its state. This perspective naturally invites a hypothesis that has captured the public imagination. Could our universe be a simulation? While often dismissed as science fiction, some theoretical physicists and philosophers argue that if the universe is indeed fundamentally computational, then the simulation hypothesis becomes a logically coherent, if currently unprovable, possibility. The argument isn't that some advanced alien species is running our universe on their version of a supercomputer. Rather, it's that the underlying nature of reality might be intrinsically digital and computational. The quantum fluctuations, the probabilistic outcomes, the discrete quanta of energy, these could be seen as the cosmic equivalent of pixels and processing cycles. Of course, this remains a highly speculative idea far from the scientific mainstream, and it raises more philosophical questions than it answers. But its power lies in how it leverages the principles of quantum information theory to reframe the age-old question of what is real. It suggests that the most fundamental reality might not be material but informational, and that the universe is, at its heart, a magnificent and self-sustaining quantum computation, whose output is everything we see, feel, and are. Imagine the serene surface of a perfectly still pond, a mirror reflecting the sky above. Now picture dropping a single stone into its center. The impact sends out a series of ripples, expanding in perfect circles, warping the reflected image of the clouds and trees. These ripples are energy traveling across the two-dimensional surface of the water. Now take that concept and elevate it to the grandest possible scale. Replace the pond with the four-dimensional fabric of spacetime itself, and replace the stone with the most violent, energetic events in the entire cosmos. The ripples generated by these cataclysms are what we call gravitational waves, and their detection has opened an entirely new window onto the universe, one that allows us to hear the echoes of quantum events from the dawn of time. For a century, gravitational waves were a spectacular prediction of Einstein's general theory of relativity, a beautiful but unproven mathematical consequence of his description of gravity as the curvature of spacetime. Einstein himself wondered if they would ever be detected, as their effects are almost unimaginably tiny. The theory states that any accelerating mass should generate these ripples, but to create waves strong enough to travel across the universe and be measured, you need astronomical violence on an epic scale. Think of two black holes, each with a mass tens of times that of our Sun, locked in a final, deadly dance. As they orbit each other at a significant fraction of the speed of light, they churn the spacetime around them, sending out powerful undulations in all directions. When they finally collide and merge into a single, more massive black hole, an enormous burst of energy is released in the form of gravitational waves. In that instant, for a fraction of a second, the merger can outshine the combined light of every star in the observable universe, but all that energy is emitted as gravity, not light. The first direct detection of these waves in September 2015 by the LIGO Observatory was a monumental human achievement, confirming Einstein's final major prediction and earning a Nobel Prize. It was the sound of two black holes, one 29 and the other 36 times the mass of the Sun, merging over 1 billion light-years away. But this was just the beginning. Since then, we have heard the gravitational wave chirps from colliding neutron stars, events that also flash with light across the electromagnetic spectrum, giving us a multi-messenger view of cosmic collisions. Each detection is like adding a new instrument to a cosmic orchestra, allowing us to hear the universe in a way we never could with light alone. We are no longer just stargazers, we are now also listeners, tuning in to the symphony of spacetime itself. Yet, the most profound connection lies not in these recent stellar crashes, but in waves that are far, far older and much, much quieter. To find them, we must rewind the cosmic film all the way back to the universe's first infinitesimal moments, to the period of rapid inflation. As we've explored, the infant universe was a seething quantum foam, buzzing with fluctuations dictated by the uncertainty principle. The violent expansion of inflation didn't just stretch these quantum jitters into the seeds for galaxies, it also shook the very fabric of spacetime with incredible force. This shaking would have generated a background sea of primordial gravitational waves, washing through the entire cosmos ever since. These waves are not from a single event in space. They are a fossil imprint from the birth of spacetime, a relic from the universe's first moment of existence. This is where the quantum story and the cosmic story become inseparable. The strength and pattern of these primordial gravitational waves are a direct reflection of the energy scale at which inflation occurred. That energy scale is intimately tied to the world of quantum gravity. Detecting these waves would be like finding the cosmic equivalent of a fingerprint, and that fingerprint would have been left by the quantum processes that powered inflation itself. It would be the most direct evidence possible that gravity has a quantum nature, showing that the fabric of spacetime itself was once subject to the same quantum rules that govern particles. The search for this signal is one of the most intense pursuits in all of cosmology, often called the hunt for the smoking gun of inflation. The primary method for this search involves scrutinizing the cosmic microwave background, the afterglow of the Big Bang. As these primordial gravitational waves traveled through the early universe, they would have subtly influenced the polarization of this ancient light, creating a distinct, swirling pattern known as B-mode polarization. Finding this specific pattern in the CMB would be the telltale sign. Initial excitement from the BICEP-2 collaboration in 2014 was later tempered when it was determined that interstellar dust could mimic the signal. But the hunt continues with ever more sensitive instruments, like the Simons Observatory and the proposed Lightbird satellite, which are designed to distinguish the faint whisper of primordial waves from the dusty foreground of our own galaxy. Detecting this signal would do more than just confirm a theory. It would provide a direct measurement of the energy that drove the universe's incredible growth spurt. It would tell us what kind of quantum field, what kind of physics, was in command during that first fraction of a second. It would offer us a glimpse into the era where the quantum world and the gravitational world were unified, a regime we cannot hope to recreate in any particle collider on Earth. Gravitational waves, therefore, are the ultimate time machine. The ones from black holes tell us about the universe's recent, violent history, but the primordial ones would carry a message from the very edge of time, a whisper from the quantum vacuum that gave birth to everything we see. They are the ripples from the very first stone dropped into the pond of spacetime, and we are now, finally, learning how to listen for their faint and ancient echo. But if the universe truly is a quantum system at its core, governed by a universal wave function, then we are forced to confront one of the deepest and most perplexing questions in all of science. What causes this cloud of possibilities to condense into a single, definite reality? This is the essence of the measurement problem, the central enigma that lies at the heart of quantum mechanics and forces us to question the very nature of reality itself. The problem is starkly simple to state but fiendishly difficult to solve. The mathematical framework of quantum mechanics, the Schrödinger equation, describes a system evolving in a smooth, deterministic way, existing in a superposition of many possible states. But when we perform a measurement, we always find the system in one specific state. The elegant, continuous wave function seems to suddenly and discontinuously collapse. The equations offer no mechanism for this collapse. It is simply postulated as an axiom, an add-on to the theory. This raises a profound question. What exactly constitutes a measurement, and why does it have this special, reality-defining power? Over the decades, physicists and philosophers have proposed a variety of interpretations to solve this riddle, each with its own startling implications for the nature of existence. The most historically prominent is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. In this view, a quantum system does not possess definite properties until it is measured. The act of observation by a classical apparatus, or by extension, a conscious observer, is what forces the wave function to collapse, bringing a specific reality into being. This interpretation draws a sharp line between the quantum world, which is fuzzy and probabilistic, and the classical world of definite outcomes. However, it famously refuses to define what qualifies as a measurement, leaving the process of collapse somewhat mysterious and placing the observer in a strangely privileged position. In stark contrast, the many worlds interpretation proposed by Hugh Everett eliminates the collapse entirely. It takes the mathematics of quantum theory at face value. Every time a quantum system has multiple possible outcomes, the entire universe splits into branches, each containing one of the results. In this view, the wave function never collapses. It just continuously evolves, and every possible outcome physically occurs in its own separate, non-communicating universe. There is no special role for measurement or observation. The reason we only experience one outcome is simply because our consciousness is split along with the universe, following a single branch of the endlessly forking tree of possibilities. While this avoids the mysterious collapse, it demands we accept the breathtaking existence of an infinite multitude of parallel realities. Other interpretations seek a middle ground. Objective collapse theories propose that the wave function collapse is a real physical process, not caused by observation, but triggered spontaneously when a system becomes too large or complex. In these models, a new, fundamental law of nature causes superpositions to break down on their own after a certain scale, providing an objective threshold between the quantum and classical realms. Then there is the relational interpretation, which argues that quantum states are not absolute but are always defined relative to another system. There is no single, God's eye view of the universe. Properties only exist in relation to other things. An electron has a definite position only in relation to, say, a measuring device, not in any absolute sense. Reality, in this view, is a network of relationships rather than a collection of independent objects. This leads to a fascinating and highly speculative cosmic question. If observation plays a role in defining reality at the quantum scale, could the entire universe, in some sense, require an observer? This idea, explored by physicist John Archibald Wheeler in his participatory anthropic principle, suggests that observers are necessary to bring the universe into existence. In his famous delayed choice thought experiments, Wheeler showed how a decision made by an observer in the present could seemingly retroactively determine the past behavior of a particle. He playfully suggested that we live in a participatory universe, where the act of observation is a vital part of the cosmic process, and that the universe has developed in such a way as to eventually produce observers who would look back and, in a sense, give it concrete reality. This is not to suggest a human-centric universe, but rather that consciousness or information gathering might be a fundamental feature of physical law. A more modern and less mystical approach to bridging the quantum-classical divide is the theory of quantum Darwinism, developed by Wojciech. This framework explains the emergence of the classical world from the quantum through the process of decoherence and environmental interaction. When a quantum system interacts with its environment, be it photons, air molecules, or any other surrounding particles, information about the system is copied and redundantly imprinted onto the environment. Multiple observers can then independently measure the system by accessing these widely disseminated copies in the environment, and they will all agree on the same outcome. This proliferation of information is a form of natural selection. The states that are most robust and can create the most copies are the ones we perceive as classical, objective reality. In this view, there is no mysterious collapse. The definite world we see emerges because we, as observers, are only able to access a small, classical slice of the information available, the part that has been repeatedly duplicated and made stable by its interactions with the rest of the universe. The quantum weirdness is still there, but it is hidden from our view like the submerged part of an iceberg. This idea beautifully explains why we all agree on the position of the moon or the chair in the room, not because it is inherently classical, but because its quantum information has been broadcasted and made objective through countless interactions. While these ideas about observers and the cosmos are controversial and far from settled science, they force a radical expansion of our perspective. They encourage us to consider that the quantum rules governing particles might indeed apply universally, from the smallest subatomic flicker to the largest galactic cluster. The transition from possibility to actuality might not be a boundary we cross, but a relationship we enact through interaction. It suggests that reality might not be a static, pre-existing collection of things, but a dynamic and participatory process, a universe that is not just seen, but is also seeing itself through us, in a grand, collaborative dance of existence that defines everything from the spin of an electron to the orbit of a planet. From the strange rules governing particles to the vast fate of the cosmos, there is a profound and often overlooked connection that ties everything together, a concept that dictates the very direction of existence itself. This is the arrow of time, the undeniable fact that the past is fixed and the future is open, that eggs scramble but never unscramble, and that we remember yesterday but not tomorrow. For centuries, this flow of time was a puzzle, but the key to understanding it lies at the intersection of two seemingly unrelated fields, quantum mechanics and thermodynamics. Their meeting point is a concept called entropy, a measure of disorder that always increases in an isolated system, creating the one-way street we experience as the passage of time. To grasp how this works, we need to start not with the universe, but with the behavior of a single particle. In the quantum world, particles can exist in a state of pure coherence, like a perfectly synchronized choir where every singer is in tune and in time. This is a state of low entropy, a highly ordered and delicate condition. An electron in a superposition of spinning both clockwise and counterclockwise is a simple example. But this pristine quantum order is incredibly fragile. The moment this particle interacts with its environment, be it a stray photon, an air molecule, or a measuring device, it undergoes a process called decoherence. Those perfectly coordinated quantum waves become scrambled and out of phase with each other. The superposition collapses into a definite state, and the information about the original, delicate coherence is spread out irreversibly into the environment. This is the quantum version of increasing entropy. The system has moved from a state of exquisite order to a state of disorder, and this process is happening trillions of times every second all around us. It is the microscopic engine that drives the arrow of time forward, one quantum interaction at a time. Now, let's pull our perspective back to the grandest possible scale, the origin of the entire universe. When we look back to the Big Bang, we find a cosmic mystery that is the ultimate expression of this idea. The early universe was in a state of astonishingly low entropy. It was hot and dense, but it was also incredibly smooth and uniform. Imagine a brand new deck of cards perfectly sorted by suit and number. This is a highly ordered, low entropy state. If the universe had begun in a state of high entropy, a completely random, disordered mess, gravity would have had nothing to work with. Matter would have been evenly distributed, and no stars, galaxies, or planets could ever have clumped together. The fact that we exist is direct proof that the universe started with this very specific, very special low entropy configuration. So why was the entropy so low? This is one of the deepest questions in all of cosmology, and the answer may lie in the quantum nature of the cosmos itself. The prevailing theory is that the universe began as a tiny quantum fluctuation, a random event emerging from a broader multiverse or a previous cosmic phase. In this view, our entire cosmos could be one small bubble that nucleated with a very specific, low-entropy initial condition. The smoothness of the early universe, which later became the source of all structure, might have been set by quantum uncertainty, a random but incredibly fortunate roll of the quantum dice that gave us a universe capable of complexity and life. The low entropy of the Big Bang wasn't a violation of the laws of thermodynamics. It was the ultimate starting condition, the first domino whose fall set in motion the entire irreversible chain of events that led to us. This initial state set the cosmic clock ticking, and it dictates the ultimate fate of everything. The second law of thermodynamics points us toward the heat death of the universe, a distant future where entropy has reached its maximum. Stars will burn out, black holes will evaporate over eons, and matter itself will decay, leaving behind a cold, dark, and utterly uniform sea of particles where no further work can be done and no meaningful events can occur. It is the final state of maximum disorder, but could quantum mechanics offer a way out of this bleak, frozen end? Some speculative theories for a cyclic or bouncing universe suggest yes. In models like loop quantum cosmology, the Big Bang might not have been a true beginning, but a big bounce from a previous universe that had collapsed. In this scenario, the transition through the quantum gravity epoch could have somehow reset the entropy clock, allowing for a new cycle of structure and complexity to begin anew. While this remains highly theoretical, it opens the door to a fascinating possibility that quantum processes operating at the smallest scales might not only set the arrow of time in motion, but could also, in the most extreme conditions, wind the cosmic spring once again. Imagine the entire universe you know and love. Every galaxy, every star, every person confined to the surface of a single, impossibly thin membrane, floating like a ghostly sheet in a higher dimensional space we cannot see or touch. This isn't a premise for a science fiction novel. It is a serious and mathematically elegant proposal from one of the leading candidates for a theory of everything. String theory cosmology asks us to take a leap of imagination, to envision that the three dimensions of space we experience are not the entire story. The theory's starting point is as simple as it is revolutionary. The fundamental building blocks of reality are not zero-dimensional points, but tiny, vibrating one-dimensional loops of energy. Each distinct vibration mode of these strings corresponds to a different particle. One note might be an electron, another a photon, and crucially, one particular vibration gives rise to the graviton, the hypothetical quantum carrier of gravity. In this single, breathtaking move, gravity is no longer an outsider to the quantum world. It is woven into the very fabric of the theory. a natural and inevitable consequence of a string's harmonic oscillations. For this beautiful mathematical symphony to work, however, it requires a much larger concert hall than the one we perceive. The equations of string theory are only consistent in a universe with 10 or 11 dimensions of spacetime. This immediately presents a profound question. If there are more dimensions, where are they? Why do we only experience 3 of space and 1 of time? The answer lies in a process called compactification. The extra dimensions are theorized to be curled up into incredibly tiny, complex shapes at every single point in space, far too small for us to ever directly detect. A helpful way to visualize this is to think of a garden hose. From a great distance, it looks like a simple one-dimensional line, but if you were an ant crawling on its surface, you would discover it has a second dimension, its circular circumference. In the same way, at every location in our familiar three-dimensional space, there could be 6 or 7 extra spatial dimensions curled into an intricate, multi-dimensional shape called a Calabi-Yau manifold. The specific way these dimensions are folded is not arbitrary. It determines the very laws of physics in our universe. The mass of the electron, the strength of the forces, the number of particle families, all of these fundamental properties could be locked into the geometry of these hidden dimensions, making string theory not just a theory of particles, but a theory of why the universe has the particular rules that it does. This idea leads to one of the most dramatic cosmological implications of string theory, the brane-world scenario. The theory suggests that these fundamental strings can be open with endpoints or closed like loops. The endpoints of open strings are not free to wander the full higher dimensional space. They are pinned to dynamic surfaces called Dirichlet branes, or D-branes for short. Our entire observable universe, with all its stars, planets, and forces except for gravity, could be such a D-brane, a three-dimensional membrane existing within a higher dimensional bulk. In this picture, the particles of the standard model are like open strings whose endpoints are stuck to our brain, which is why we are confined to it and cannot perceive or access the other dimensions directly. Gravity, however, is carried by closed strings, which have no endpoints and are therefore free to propagate through the entire bulk. This could provide a stunning explanation for why gravity is so phenomenally weaker than the other fundamental forces. Its influence is not concentrated on our brain but diluted throughout the full volume of the higher dimensional space. We only feel a faint shadow of its true strength, solving the long-standing hierarchy problem that has puzzled physicists for generations. The brane-world concept also offers radical new ways to think about the universe's history. Cosmic inflation, the period of hyper-expansion after the Big Bang, might be explained as the result of 2 branes moving through the bulk. Imagine our universe as one membrane and a parallel universe as another, separated by a tiny gap in a higher dimension. The energy released as these 2 branes collided could have been the spark that ignited the Big Bang itself, in a scenario known as the ekpyrotic universe model. This replaces the idea of a singular beginning with a cyclic or bouncing cosmology, where our universe is part of an eternal cycle of collisions in a higher dimensional space. Furthermore, the mysterious dark energy that is accelerating the expansion of our universe could be explained by a new force associated with the tension of our brain or the energy of the vacuum in the bulk, offering a potential pathway to calculate its value from first principles, something that has so far eluded conventional physics. While the mathematical beauty of string theory is undeniable, it faces a significant challenge. The vast number of possible ways to compactify the extra dimensions leads to a stupendous number of possible vacuum states, perhaps as many as 10 to the 500th power. This is the string theory landscape, a cosmic array of potential universes, each with different physical constants and laws. In a multiverse context, this isn't necessarily a weakness but a feature. It provides a framework for understanding the apparent fine-tuning of our universe, suggesting we simply inhabit one of the rare bubbles where the compactification yielded laws suitable for life. The journey of string theory cosmology is a testament to human imagination, asking us to conceive of a reality with hidden depths and dimensions, where the cosmos we see is just a slice of a far richer, more complex, and more interconnected existence, all unified by the vibrational music of tiny strings. But what if the story we've been telling ourselves about the absolute beginning of everything is fundamentally incomplete? The classical Big Bang model presents us with a terrifying singularity, a point of infinite density where the laws of physics simply break down and all our equations spit out nonsensical answers. It's the ultimate cosmic dead end, a barrier beyond which science cannot see. Yet this very barrier might be an illusion, a sign that we are missing a crucial piece of the puzzle. What if, instead of a singular beginning, our universe was born from a prior cosmic phase, in a magnificent rebound that echoes the cyclical patterns we see throughout nature? This is the revolutionary promise of loop quantum cosmology, a theory that dares to rewrite the very first chapter of cosmic history by applying the granular nature of quantum geometry to the entire universe. At its heart, loop quantum cosmology is an application of the broader theory of loop quantum gravity to the specific conditions of the cosmos. Remember, loop quantum gravity proposes that spacetime isn't a smooth, continuous fabric, as Einstein described, but is instead woven from tiny, indivisible loops, a network of a billion individual threads of spacetime. This granular structure introduces a fundamental limit to how small things can get, a smallest possible scale known as the Planck length. In the classical Big Bang model, as we rewind time, the universe gets smaller and hotter and denser until it reaches a point of zero volume and infinite density. But in a universe made of discrete quantum grains, you cannot compress things to a true zero. It's like trying to divide a crowd of people into a space smaller than a single person. It's simply impossible. The quantum nature of spacetime itself acts as a sort of cosmic repulsive force, which becomes overwhelmingly powerful at these extreme densities. Instead of collapsing into a singularity, the universe reaches a maximum possible density and then rebounds, bouncing into a new phase of expansion. The Big Bang is replaced by a big bounce. This single shift in perspective transforms our entire cosmic narrative. We are no longer dealing with a universe that popped into existence from nothing for no reason. Instead, we are likely part of a cyclic or eternal cosmos, with a history that extends back long before what we call the Big Bang. Our expanding universe could be just the latest chapter in an endless series of contractions and expansions, a cosmic heartbeat pulsing through eternity. Each cycle would begin with a bounce from a previously contracting universe, filled with its own galaxies, stars, and perhaps even life, all compressed and transformed in the quantum furnace of the bounce. This doesn't necessarily mean the cycles are identical. Each bounce could completely reshuffle the fundamental constants and laws, or it could preserve some quantum information from the previous eon, creating a subtle inheritance from one universe to the next. One of the most thrilling aspects of this theory is that it might leave behind observable evidence, a faint fingerprint from the universe that existed before our own. As the pre-bounce universe contracted, it would have been filled with gravitational waves and other radiation. During the violent quantum bounce, these ripples in spacetime could have been imprinted onto the new, expanding universe. While the intense heat of the early cosmos would have wiped clean most information, some cosmologists speculate that the very largest structures, the biggest patterns in the cosmic microwave background, might still carry a subtle, statistical signature of that pre-bounce era. It's a long shot, but future ultra-precise maps of the CMB, from missions even more sensitive than the Planck satellite, could one day go looking for these ghostly echoes from a time before time, searching for an anomaly in the data that whispers of a cosmos that came before. This profound idea beautifully illustrates the core mission of bridging the quantum and the cosmic. The solution to the greatest mystery of cosmology, the origin of the universe, is found not by building a bigger telescope, but by looking deeper into the quantum nature of reality. The tiny, discrete loops of quantum geometry, acting on the smallest imaginable scale, produce a repulsive force powerful enough to reverse the collapse of an entire universe and trigger a new birth. The micro directly dictates the macro. The quantum graininess of spacetime isn't just a curiosity of tiny particles. It is the very mechanism that may have saved the cosmos from a singular death and set it on the path to creating everything we see around us, offering a vision of an eternal, perhaps infinite, universe with no true beginning and no definitive end. For decades, the hunt for dark matter has been one of the most compelling and frustrating quests in all of science. We know it's out there. Its gravitational pull is the invisible hand that sculpts galaxies and binds clusters together, but it has remained utterly elusive, refusing to interact with light or any form of ordinary matter in a way we can easily detect. Confronted with this ghostly adversary, physicists have been forced to become cosmic detectives, building traps of unimaginable sensitivity. And in this high-stakes investigation, the most powerful tools at our disposal are no longer just massive telescopes. They are exquisitely engineered instruments that harness the bizarre laws of the quantum world to catch a particle that may have been flowing through us since the beginning of time. The challenge is immense. If dark matter particles are indeed weakly interacting massive particles, their interactions would be incredibly rare and feeble. Imagine trying to hear a single pin drop in the middle of a hurricane. To have any hope of success, experiments must be shielded from the constant background noise of the universe. This is why the most sensitive detectors are buried deep underground, in abandoned gold mines or beneath mountains, where thousands of feet of solid rock absorb the cosmic rays that would otherwise bombard and overwhelm the experiment. But even in this profound silence, the signal would be vanishingly small. This is where quantum ingenuity takes over. Experiments like LUX Zeppelin, the reigning champion in sensitivity, are marvels of quantum engineering. At its heart is a colossal vat of ultra-pure liquid xenon, chilled to -100 degrees Celsius. If a WIMP, having passed effortlessly through the Earth above, were to drift into this tank and rarely bump into a xenon nucleus, the collision would produce two telltale signals, a tiny flash of scintillation light and a handful of freed electrons. To detect this infinitesimal event, the experiment uses photomultiplier tubes, exquisitely sensitive devices that can amplify a single photon into a measurable electrical pulse. The freed electrons are then drifted upward by a powerful electric field into a thin layer of xenon gas, where they produce a second, larger flash of light. This two-phase system, relying on the quantum properties of xenon atoms, allows physicists to precisely pinpoint the energy and location of an interaction, and crucially, to distinguish a potential WIMP signal from residual background noise. It is a perfect example of using quantum effects, the emission and amplification of light from atomic collisions, to listen for the faintest whisper in the dark. But as the search for WIMP has continued to return null results, despite ever-increasing sensitivity, attention has shifted dramatically toward a different, even more ghostly candidate, the action. This hypothetical particle was originally proposed to solve a completely unrelated problem in particle physics. but has since become a leading dark matter contender. Actions would be billions of times lighter than electrons, behaving less like discrete bullets and more like a pervasive, invisible wave oscillating through the cosmos. To detect something so ethereal, physicists must once again turn to quantum tricks, this time with a setup that feels like it's straight out of a quantum magician's playbook. The Action Dark Matter Experiment, or ADMX, doesn't try to catch a particle in a tank. Instead, it uses a powerful superconducting magnet to create a strong magnetic field. The theory suggests that within this field, an action could, under the right conditions, convert into a microwave photon. To find this one specific photon, the experiment uses a high-quality resonant cavity, essentially a sophisticated microwave oven, that can be tuned to different frequencies. Inside this cavity, cooled to near absolute zero to eliminate thermal noise, the team listens for a faint, persistent tone at a specific frequency, the quantum note that would signal an action's conversion. It's an incredibly delicate process, akin to tuning a radio across the entire dial in the hopes of finding one unique station broadcasting from the dawn of time, with a signal so weak it could be easily drowned out by the slightest interference. These recent null results, while disappointing to some, are far from failures. In science, not finding something is itself a powerful result. Each experiment that fails to detect WIMP or actions at a predicted sensitivity level helps to carve away vast regions of possibility. It tells theorists that their models need to be refined, that dark matter might be even stranger and more weakly interacting than we thought, or that we must broaden our search to other, more exotic possibilities. The absence of a signal is actively reshaping the theoretical landscape, pushing us to think more creatively about the true nature of the universe's missing mass. This iterative process where theory motivates ever more sensitive experiments and experimental results circle back to refine theory is the very engine of scientific discovery. The quantum technologies developed for this hunt, from ultra-sensitive photon detectors to quantum-limited amplifiers, are not just solving a cosmic mystery, they are pushing the entire frontier of measurement science, creating new capabilities that will benefit fields from medicine to materials science. The quest to identify dark matter is more than a Chinese letter pursuit. It is a testament to human curiosity and ingenuity, demonstrating that to uncover the largest secrets of the cosmos, we must first master the smallest details of the quantum realm. Yet as we stand on the precipice of these staggering discoveries, peering into the quantum code that may underpin all of reality, we are compelled to pause and ask a question that transcends pure science. Just because we can unlock these secrets, does it mean we should? The pursuit of knowledge, especially knowledge this profound, is never without consequence, and the ethical dimension of understanding the quantum cosmos is as vast and complex as the subject itself. This isn't just abstract philosophizing. The potential applications of this knowledge could reshape human civilization in ways we are only beginning to imagine, carrying with them equally immense promises and perils. Consider the transformative power of quantum technologies already on the horizon. Quantum computers, which leverage superposition and entanglement, promise to revolutionize fields from medicine to materials science. They could help us design new life-saving drugs by simulating complex molecular interactions with perfect accuracy, or develop room-temperature superconductors that would make our energy grid perfectly efficient, effectively solving the climate crisis. The ability to precisely engineer matter at the quantum level could lead to materials with previously unimaginable properties, metals that are both lighter and stronger than anything we have, or medical nanobots that can repair our bodies from within. The positive potential for human health, environmental sustainability, and technological progress is nothing short of miraculous. But the same principles that could cure diseases could also crack the digital foundations of our society. A sufficiently powerful quantum computer would effortlessly break the encryption protocols that currently secure every financial transaction, every piece of private communication, and every government secret on the planet. This wouldn't just be a nuisance, it would be an immediate and catastrophic threat to global economic and national security, rendering our current digital world completely vulnerable. The race for quantum supremacy is therefore also a race for quantum resilience, a desperate effort to develop new, quantum-proof encryption before the old ones are shattered. This dual-use nature of the technology, a tool for incredible good and potentially devastating disruption, is a classic ethical dilemma amplified to a global scale. And this is just the technology we can foresee. The real ethical challenges may come from applications we haven't even conceived of yet. Looking further into the speculative future, the stakes become almost unimaginable. If a theory of quantum gravity were to grant us a deeper understanding of spacetime itself, could it one day open the door to technologies that seem like pure magic today? The manipulation of gravitational fields or even the theoretical concept of warp drives, while firmly in the realm of science fiction now, would have staggering implications. The energy requirements and material science needed for such endeavors would be beyond anything we currently possess, potentially creating a civilization with God-like control over the fabric of the cosmos. But who would control such technology? The potential for misuse, whether in the form of unprecedented weapons or tools for geopolitical domination, is terrifying. The very knowledge that allows us to understand the origin of the universe could also grant a single entity the power to alter it on a fundamental level, raising ethical questions we are completely unprepared to answer. Beyond the tangible threats of weapons and broken encryption, there is a more subtle yet equally profound societal risk, the potential for radical insights to disrupt our collective worldview. The Copernican revolution displaced us from the center of the universe. Darwinian evolution placed us within the animal kingdom. A complete understanding of the quantum cosmos could deliver a third, equally humbling blow. If the multiverse hypothesis were proven true, for instance, it could fundamentally alter our perception of our place in existence, suggesting our universe is one of countless others, rendering our story both insignificant and statistically inevitable. While for some this is a liberating idea, for others it could be deeply unsettling, potentially challenging long-held religious, spiritual, and philosophical beliefs that have provided meaning and moral frameworks for millennia. The responsible dissemination of such world-shattering knowledge would be a monumental task, requiring careful public engagement and dialogue to avoid widespread existential anxiety or a dangerous cultural backlash against science itself. This is why the journey into the quantum cosmos cannot be undertaken by scientists alone. It demands a new model of open and inclusive stewardship, a collaboration between physicists, ethicists, philosophers, policymakers, and the public. The old model of scientific discovery, working in isolated labs and publishing results for a specialized community, is inadequate for knowledge this powerful. We need to build ethical frameworks and international agreements alongside the research, not as an afterthought. The lessons from the development of nuclear technology are a sobering reminder of what happens when transformative science outpaces our ethical and political preparedness. The goal must be to avoid a new quantum arms race and instead foster a global commitment to using this knowledge for collective benefit, ensuring that the fruits of understanding the universe are used to elevate humanity, not to divide or destroy it. The greatest responsibility for today's physicists and cosmologists is not just to uncover the secrets of the cosmos, but to ensure that in doing so, we strengthen our humanity, our empathy, and our commitment to a future where this breathtaking knowledge serves life rather than threatens it. The quest to understand the quantum cosmos is often portrayed as the solitary work of physicists, toiling away with complex equations and massive telescopes. But this could not be further from the truth. Unraveling the deepest mysteries of the universe is perhaps the most profoundly collaborative human endeavor, a symphony of insight where the melodies of mathematics, the rhythms of computer science, the harmonies of philosophy, and even the counterpoints of biology all come together to compose a richer, more complete picture of reality. This interdisciplinary conversation is not a luxury. It is an absolute necessity, for the universe does not respect the artificial boundaries we have drawn between our fields of study. Mathematics provides the fundamental language for this entire conversation, and nowhere is this more evident than in the application of topology to our understanding of spacetime. Topology is often called rubber sheet geometry because it is less concerned with precise distances and angles and more with the fundamental, unchanging properties of a shape, like how many holes it has. You can twist and stretch a coffee mug, and to a topologist, it remains equivalent to a donut because both have a single hole. This abstract field is now absolutely crucial in quantum cosmology. For instance, the theory of cosmic inflation suggests that the entire observable universe may have expanded from a tiny, topologically non-trivial fluctuation in the primordial quantum foam. The way these spacetime bubbles nucleate and expand is governed by topological principles. Furthermore, in string theory, the way the extra dimensions are curled up is described by Calabi-Yau manifolds, complex shapes whose topological properties directly determine the physical laws like the number of particle generations and the strength of forces within that universe. Mathematics is not just a tool for calculation here, it is the very canvas upon which the picture of physical reality is painted, revealing possibilities that pure physical intuition might never have discovered. Stepping from abstract math to practical application, computer science has become the indispensable laboratory for the theoretical cosmologist. The equations describing the quantum birth of the universe or the evolution of the cosmic web of dark matter are so complex that they are utterly unsolvable by hand. This is where supercomputers and sophisticated algorithms take over. Cosmologists now run massive numerical simulations that model the entire history of the universe, from its quantum fluctuations to the formation of billion-sun galaxies. They use techniques like n-body simulations to track the gravitational dance of trillions of particles, each representing a clump of dark matter, but the connection is growing even deeper with the rise of machine learning. The vast, complex datasets from telescopes like the James Webb Space Telescope or the Vera C. Rubin Observatory are so enormous that traditional analysis is impossible. Scientists are now training artificial neural networks to find subtle patterns in this data, to classify unusual galaxies, or even to generate synthetic universes to test different cosmological models against the real one. In a beautiful feedback loop, the same quantum-inspired algorithms that power machine learning are now being used to understand the quantum-inspired structure of the cosmos itself. This relentless drive for understanding inevitably pushes us from the how into the realm of the why, and this is where philosophy reclaims its ancient role as a partner to cosmology. The bizarre conclusions of quantum mechanics and the staggering implications of the multiverse hypothesis force us to confront foundational questions about the nature of reality, knowledge, and existence that have been debated for millennia. What does it mean for something to be real if its properties are indefinite until measured? Does the many worlds interpretation imply an ontological reality for all possible universes, or is it merely a useful mathematical formalism? Philosophers of science work alongside physicists to clarify these concepts, to analyze the logical structure of theories, and to explore the limits of scientific inquiry itself. They help physicists navigate the complex relationship between mathematical beauty and physical truth, and to understand the implications of a universe that may be fundamentally informational rather than material. This collaboration ensures that the scientific revolution in physics is matched by an equally profound revolution in our comprehension of what it all means. Perhaps most surprisingly, even biology is beginning to whisper its insights into the cosmic conversation, particularly through the lens of complexity and emergence. Biological systems are masterclasses in how simple rules and local interactions can give rise to incredibly complex, ordered, and adaptive behavior, from a colony of ants to the neural network of a human brain. This study of complex systems provides fascinating analogies for cosmologists studying how the simple, elegant laws of quantum physics gave rise to the breathtaking complexity of the cosmic web. The patterns of galaxy filaments and voids bear a striking, though not identical, resemblance to neural networks in the brain or the growth patterns of slime molds. This isn't to say the universe is a brain, but rather that there may be universal principles of self-organization that operate across vastly different scales and systems. Understanding how complexity emerges in one domain can provide powerful intuitions and new mathematical tools for understanding it in another, suggesting a deep unity in the laws that govern complex systems, from the biochemical to the cosmological. This magnificent tapestry of shared knowledge shows us that the bridge between the quantum and the cosmic is not being built by physicists alone. It is a collective effort, a testament to the unity of human curiosity. A topologist's theorem, a computer scientist's algorithm, a philosopher's rigorous question, and a biologist's model of emergent order all provide essential threads. They remind us that the universe is one interconnected whole, and that to understand its deepest secrets, we must be willing to listen to every dialect in the language of discovery, weaving them together into a story that is as rich and multifaceted as reality itself. So as we reach the end of our journey, let's take a moment to look back at the breathtaking landscape we've traveled. We began with a universe divided, a cosmos where the rules for the tiny quantum realm seemed utterly separate from the laws governing galaxies and gravity. But through our exploration, we've witnessed the profound and beautiful threads that weave these worlds together into a single, magnificent tapestry of reality. We saw how the bizarre principle of quantum superposition isn't confined to a lab. It's the very mechanism that, when stretched by cosmic inflation, planted the gravitational seeds for every galaxy, star, and planet we see today. We grappled with the spooky connection of entanglement and discovered it might be the cosmic glue that holds the fabric of spacetime together, linking distant parts of the universe in a way that defies our classical intuition. From the inherent uncertainty at the heart of all things to the wave-particle duality that challenges the nature of reality itself, we've seen how the quantum code is written into the grandest structures of the cosmos. This convergence is more than just an academic curiosity. It is the essential next step in our understanding of existence. To see the universe as anything less than a unified quantum cosmos is to have an incomplete picture, like trying to appreciate a symphony by listening to only one section of the orchestra. The journey from the historical divergence of physics to today's thrilling convergence represents one of the greatest intellectual adventures in human history. It's a testament to our relentless curiosity, our drive to peek behind the curtain of the universe and see how it all truly works. And the most exciting part is that this story is still being written. The tools we're building, from quantum computers and next-generation telescopes to the vast collaborative efforts of minds across the globe, are opening windows into realities we've only just begun to dream of. We are on the cusp of discoveries that will undoubtedly rewrite our textbooks and, more importantly, reshape our very conception of what is possible. It brings to mind the timeless words of Carl Sagan, who reminded us that somewhere, something incredible is waiting to be known. That sense of wonder, that promise of discovery, is what fuels this entire endeavor. The quantum cosmos is that incredible something, and we are the generation privileged to begin truly knowing it. This isn't a journey that ends here, it's an invitation. An invitation to stay curious, to keep asking the big questions, and to never lose that sense of awe for the strange and magnificent universe we call home. We want to hear your thoughts and your questions in the comments below. What part of this quantum cosmic bridge fascinated you the most? If you enjoyed this deep dive, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the mysteries of the universe. The greatest discoveries are still ahead of us, and we can't wait to continue